All right. Hello and welcome, lads and ladettes. Today we're going to be getting into another null hypothesis episode. And for those who are new to the null hypothesis method, it's the classic Karl Popper method of falsifying the null hypothesis to show that your main hypothesis is likely the true one. So the way that we like to do it is we'll set the H naught to be the thing that is assumed to be true or correct, and then we will try to falsify the opposite, the mutually exclusive opposite, as our H naught. And if we fail to falsify our H naught, then our hypothesis, our H1, is likely to be invalid. So following that methodology, we did a presentation last week on Battle of the Beams, and this will be a follow-up presentation to, or I'm sorry, this will be the introduction to the second episode, which is going to be on the null hypothesis of whether or not the Earth is an inertial frame or not, and what the definition of an inertial frame is, etc. We'll get into that as we continue. Let's see here. So to start us off, I'd like to give a little summary. This is going to be a summary of the dynamic challenge that Dr. Bennett put out a couple of years ago on Witset's show when he did the interview for In the Field. And one of the arguments that was put forward really struck me, and it was through dynamic analysis, through either energy or momentum conservation, energy prediction, etc. You can show that the lab frame makes the correct prediction every time. And of course, there are other experiments that we can get into that aren't like interferometry, excuse me, and electromagnetic laws and stuff. But we'll get to those in a follow up to this. Right now, we're just focusing on the laws of dynamics and future predictions of motion, and which reference frame satisfies those conditions without any additional fictitious terms. And so I got this Jupyter note here that I'm going to read from, and then we're going to go over the math as it pops up. And then there's chunks of code that solve the math. So we'll skip over those chunks, but we'll just go off the summaries or whatnot of those. But we're going to take a look at what these formulas represent and what they provide in terms of defining, which frame is the correct frame for the predictions. So we'll get to see what the argument actually looks like when you put the figures to the formula. Okay, so let's see. So the definition of an inertial frame, to start us off with, in modernity, is defined in two ways. So the classic Newtonian way was that a object in uniform motion at a constant velocity, so no change in velocity, is defined as an inertial frame. So the way that they conceptualize Earth as kind of being like a pseudo inertial frame is that it's moving around the sun at a near constant velocity. So F equals ma will apply, and all that kind of stuff. So they say that they can treat these frames as inertial frames, and for some situations you certainly can, and they'll make all the same predictions that a true rest frame would make. But when we get into dynamic analysis, that's when certain predictions get exposed for being, non-physical. Um, so, so we'll get into that as we continue. And then, of course, the modern definition through the relativistic paradigm is still following the same uniform constant velocity as an inertial frame. So nothing really changed there in terms of the definition. They're still following that. The only thing that's changed really in terms of the physics between the two is absolute space and time. That was a Newtonian concept, and Newton didn't know where absolute space and time were, but he knew that they existed. He tried to put the absolute space in the solar system or in the stars, but it's actually, in the Earth frame. So that's what we're going to show here. And then the difference for the Einsteinian concept is time and space are not absolute; they're coordinate dependent, and they change as a function of the square of your velocity over c squared. Okay, so Newton knew it existed, didn't know where to put it. Einstein says it didn't exist. All right. Now, the alpha definition is going to be given as a frame that's truly at rest and fixed. It's not rotating or moving or doing anything at a constant velocity. Okay, so now I'm going to read from the analysis here, and we'll go over the math and such for everything. So defining the reference frame for everything. So in terms of coordinates, we're going to use the ECI frame and compare uh, things to the ECI frame. So we're going ECEF, and ECI. So here we go. So locating the inertial frame dynamic analysis. This section establishes the Earth-centered, Earth-fixed laboratory as the absolute fixed and stationary inertial frame for all mechanics. 6 standard dynamic setups are analyzed in both the ECI lab frame and a body attached to the candidate frame. In every case, only the lab frame closes the energy and force budgets natively. The candidate frame either requires fictitious forces or it returns an absurd energy to mass ratio, typically off by 10 to the 18 or 10 to the 24, because typically you have to use the opposite. So when you include Earth's mass, it ends up being a ridiculous, non-physically meaningful calculation. So reference frame and kinematics and registry. All the analysis below are using the standard scalar formulas from Newtonian mechanics and analytical mechanics as stated in the ECEF lab frame, which alpha takes as the absolute inertial frame. No fictitious forces or corrections are accepted. So in the stationary Earth model, all inertial forces are real forces. So centrifugal, Euler, Coriolis, centripetal, and centrifugal are all real forces instead of frame-dependent effects and fictitious and whatnot. So reference frames are used in this section. So both candidate frames in every comparison share the same Earth's origin center, but they differ in how their coordinate axes are treated. The ECEF, the origins is at Earth center, same as the ECI, and in the ECEF, the axis of rotation is once per sidereal day, but it's the sky that rotates, not the Earth. And the lab frame is at rest, so the lab has a rest frame velocity. And the ECEI for the observer being at the center of the Earth and comparing the rotation, that the ground rotation essentially relative to his fixed position, you would end up with something like, if someone was at the 45th latitude relative to the fictitious observer at the center of Earth, they'd be moving at 305 meters per second. In the ECI, the direction to distance in stars is approximately fixed, while the Earth is fixed. Surface location rotates beneath those directions once per sidereal day. In the ECF, the coordinates rotate with the Earth, so an Earth-fixed laboratory has zero coordinate velocity by definition, and the distant stars acquire an apparent daily motion across the sky. And all we're saying is that motion is a real motion that goes across the sky, and the Earth is fixed. So the only change is how we're interpreting the axis of rotation of the coordinate. Okay. So alpha does not redefine the ECEF as a coordinate frame. It accepts the standard Earth fixed registry literally, and the lab frame is at rest. And the observed east to west stellar sweep assigned to the celestial sphere is due to that rotation rather than the Earth itself. Okay. And then we have textbook definitions of the ECEF frame, where the surface is rotating relative to that observer at the center here. And the example of using the latitude for Paris, you would get about 305 meters per second. That's how fast the lab frame would be moving. The alpha position, the ECF frame is the absolute inertial frame. The Earth fixed frame is genuinely at rest. The east to west sweep is real. The celestial sphere actually moves westward once per sidereal day. The tangential velocity of the ECI frame attributed to a sitting body carries the lab frame, has no kinetic energy and no real momentum. A Foucault swing turnaround test confirms this empirically, as we'll go over below, where alpha predicts the kinetic energy is zero at the Bob's turnaround point, matching the measurements, while the ECI frame predicts 1.3 millijoules of unmeasured.
That would
Nope,
be
sorry,
megajoules.
that's megajoules. Yep,
Yeah.
megajoules of unmeasured rotational kinetic energy. Thank you, sir. So the ECI is a mathematical model. It is not physical reality. Consider the hypothetical minus ECEF frame, where the stars rotate in the opposite direction, eastward instead of westward. When we look at the sky, we see the opposite. The stars sweep westward, so the minus ECEF frame would be rejected by direct observation. The ECI fails the same test for the same reason and requires the stars to be at rest while the Earth is rotating, which contradicts what we actually see. So the acceleration of linear force here, so just the classic F equals ma, where you could do the acceleration is equal to the force divided by the mass. One second, I'm going to get some water. All right. F is physically real. If it is a physically sourced from a force, a mechanical contact, tension, or a real field. M is the test mass. A is the linear acceleration relative to the stationary ground. The linear momentum and conservation here. So we have P equals mass times velocity. P initial equals P final. So we have here velocity. V is the or nu is the velocity of the mass measured directly relative to the stationary ECEF ground. I'm just going to call this absolute lab frame or lab frame now as we continue. So gravitational potential energy. So your height above the ground or whatever you're referencing is going to give you potential energy. So your potential energy is defined by mass times 9.8 meters per second squared times whatever your height is. Delta in that is going to be due to the change in your height. So G is the real gravitational acceleration of 9.8 meters per second squared. H is the vertical height relative to the lab baseline. Kinetic energy configuration. Standard kinetic energy here. So we have 1/2 times mv squared. So it's just mass times velocity squared, or 1/2 of it. Um, then we have composition for adding momentums together. So we have 1/2 times the mass times the velocity squared of one frame plus the square of the relative velocity of whatever other frame. So just just simple Galilean velocity addition there, nothing too fancy. And then, of course, when we get into the analysis of a couple of the frames, it's going to require the planetary mass to be used. So what will be shown here is just the same exact scenario, so just 1/2 times the planetary mass times the velocity squared. And then we're also including a Euler-Lagrange um, analysis too. So we're going to see the uh, how that works out for the energy prediction for the system. So when we'll read through the equations here. So the L is the Lagrangian. So this is the kinetic minus the potential energy of a system, given by L equals kinetic energy minus the potential energy. Q is generalized coordinates, so position, angle, variable, just whatever starts the definitions of the system to where you're going to have your X, Y, and Z axis and all that. And then Q dot is the time derivative of the generalized coordinates here. And then, so basically, what they're doing is making like a how the energy of a system changes over time, and using that to um, derive what was it, joule meter seconds. So essentially, um, solving the trajectory of like the path, the trajectory of something in a system based on its kinetic energy and potential energy. And what's going to come out of it is the least action principle, which is going to define the energy of that system. So or how the energy unfolds over time. So suppose you have like 2 points A and B that are some distance apart, and then you're going to throw a ball to close the distance over them. And so you would take your kinetic energy and your potential energy over that system, and what would come out of that for the change in time, you would get like a parabolic arc based on that change in potential energy, with the gravitational potential. That's going to create the parabolic arc. So um, that equation of motion, that trajectory, is going to come out of solving the kinetic energy and potential energy difference over time, integrating it. So it's an extremely important concept in physics, and all the theories and predictions of future motion and all of that all have to be satisfied by this. So this is an extremely important aspect of the dynamic analysis part. Okay, and then there's the corresponding Hamiltonian, which instead of using the energy potential differences, it uses the momentum differences to derive the same thing. So it's going to derive a trajectory out of the total momentum conserved over the system, and it's not time dependent like it is like the Lagranges, and they both give the same result. So we'll be including this analysis as well as we continue. Okay. And if you guys want to like read the stuff more closely and get more in depth with it, you're totally free to do that. But there's a lot to go over here, and I'm just trying to summarize and get us through to the main arguments, and then we can get into discussion, discussion and whatnot. But I will get us through the important parts here. So let's see. Okay. Okay, yeah. So those are going to be what's going to be used for the 6 analysis per scenario that we go over. All those things that we just went over. Now to start us off, we got our starting variables here. So we got g 9.8 meters per second squared. We got mass of the Earth here. We got the daily. We got Earth's radius for when we use derive the what was it? Different latitude dependent velocities or whatever when we get to those. And then we have the sidereal rotation, and then we have well, sidereal in radians, I guess. So that's about it. Converting that into radians for sidereal time. Okay, so the color codes are going to be blue is the lab frame, inertial, or the correct amount that was measured in the lab, or the correct prediction. Pink is going to be non-inertial, or a phantom result that's going to result in energy being left over where there is not, something like that. And yellow, fictitious, is going to denote the fictitious terms that have to be added to make the frame equivalent to what the lab frame predicts. So to start us off here, we have a classic Newton's bucket, and shout out to Action Lab. He just put out a video on Newton's bucket recently. That's pretty cool. So the system by system dynamic comparison, Newton's bucket. A bucket of water is suspended by a rope and is twisted and released. The bucket spins with an angular velocity omega. The surface of the water forms a concave parabola. So here's the summary of the different analyses that we're going to be doing. The classic F equals ma, momentum, kinetic energy, and then Euler and Hamiltonian. So here's what each scenario predicts. So for the lab frame, the water at the radius r moves at a true velocity where v equals omega times r. The centripetal acceleration, alpha equals omega squared times r, requires a real radial force to supply a pressure gradient. In the bucket frame, the bucket observer would be stationary, and he would see the lab frame rotating around him. He would predict, no force. So the water co-rotates, velocity equals 0, the acceleration equals 0, so force equals 0, predicts no pressure gradient. Closes only after inserting a fictitious centrifugal force, where Fc over m equals the rotation rate squared times the radius. So you have to introduce that by hand to make the correct prediction in that frame when you're in a non-inertial frame. So for momentum, we have tangential momentum, where p theta, so the angle, is equal to mass times the rotation rate times the radius, which rotates with the element of the first derivative of momentum over the first time derivative, is equal to the mass times the angular rotation rate squared times the radius, sourced by a real pressure gradient. So, the real rotation, as noted, makes the prediction for the concave parabola. So all momentum in this frame is 0 because there's no velocity, so it has no momentum. In this frame, it is the same situation. The derivatives of d in time, the derivatives of momentum in time are equal to 0. There's no change in them. By Newton's first law, this predicts constant linear motion. Here, the water is at rest, but the bucket frame momentum bookkeeping is internally consistent for the water element at rest. But F equals ma and E and E rows show that the frame fails to predict the observed centripetal force or the parabolic surface. So when you apply those equations in that frame, you don't get the correct prediction. Same for the energy potential. So you get at the free surface, the constant pressure, the radial gravity balance integrates to the parabolic surface, and that's what you get there. Here, there's no kinetic energy potential because it's moving. So they predict that there is no change in the surface. There's an observed change, so the contradiction is there. Same when we get into the Lagrange, using cylindrical coordinates here, we find that um, that it closes natively and reproduces the parabolic surface based on the rotational vector there. But if you don't have a rotational, you know, vector, then you have you have no kinetic energy differences to solve with and stuff. So you would predict that there is no curved surface on the water unless you add a fictitious centrifugal term, which would be shown here, and that's what would get you to have the correct prediction there. And then for the Hamiltonian, for the momentum, same situation. You don't have any momentum unless you introduce this effective term, which it introduces a like a momentum potential or like a velocity, but actually it's a velocity potential. And then from that, they can extract the what the momentum would be once you insert that fictitious um, potential that has you're just interjecting it into the system because you know it has to be there, so it's not like it's not part of the system. Okay. And then a quick note on just the formalization of the equation that we're using. So we're using this one here, which is just basically allows you to use generalized coordinates for the bucket and for the surface and whatnot. So suppose you have a large bucket, or the amount of water that you're using in the bucket and all that. You could just arbitrarily define it with the coordinates given here. So using that equation, we go through the code here. When you execute the code, you get the results. Here's a nice diagram of the what's produced when the bucket is in rotation with respect to the lab frame. You get this nice concave parabola. And then here we're going to go over some figures now. So this is what the results of an analysis will look like as we move forward. 1 second, get some water. All right. So Newton's bucket numerical evaluation in both frames, so lab frame and bucket frame, are being compared. So F equals ma. So this is what creates the real pressure gradient with the rotation rate times the radial distance. We get 0.4 newtons. In the bucket frame, they're stationary. They see the lab frame moving around them. They predict no force, so their velocity is 0. So when they multiply that, they get 0. When you introduce the centrifugal fictitious force inserted by hand, you can then curve the bucket. Or I'm sorry, you can then curve the water in the bucket. For momentum, same situation. We get 0.2 kilogram meters seconds or meters per second. And then when we do what that would be for the uh, the momentum over time, we get the 0.4 newtons, the original uh, force there, which is F equals ma. And then for the bucket frame, they're still reading at 0 because they don't, they're not predicting motion here. All right, when we get into kinetic energy analysis, we get into the same situation. Uh, the bucket baseline H doesn't change, so the PE doesn't. There's no height difference there with gravity, so there's nothing predicted there. But across the board, of course, they're not moving, so they don't predict anything. So none of the values that they predict come out to predict the concave parabola. If you're in a non-inertial frame, you're going to make the wrong prediction. What we're learning so far. So following the Euler-Lagrange analysis here, with respect to the lab frame, we get the 2e minus 2 joules. And then for the bucket frame, by introducing the centrifugal and Coriolis forces there, we end up getting what's predicted uh, for the concave parabola there. Okay, but only after introducing those terms to make it correct. All right, so the centrifugal term has no real world energy source. It only exists because the bucket frame is non inertial. Without it, the Euler Lagrange in the bucket frame predicts a flat surface, contradicts reality. With it, the Euler and Lagrange recovers the parabola there, the Landau and Lifshitz parabola. They did the generalization for the coordinates. So anyway, the Hamiltonian here, they end up with the same situation because they don't have any momentum. They have to introduce a velocity potential term to match what would give the correct value for there to be a concave parabola form. All right. Now, some people will say, well, can the stars be the absolute frame? Because that was kind of what Newton said, right? He was like, maybe the absolute frame is in the old Labsky, or I'm sorry, it's in the stars, not the Labsky. Sorry. So here's an answer to that. So we'll read through here. So the bucket argument singles out the lab frame as unique, in which the F equals ma closes natively. The natural next question is whether the fixed stars could play a role in this instead. They cannot. Here's a direct answer from Dr. Bennett. I asked him recently about this. He said Newton's bucket shows that the lab frame is inertial, but the bucket is spinning. It is not inertial. By way of centripetal law, force law, but any rotation with respect to the Earth will fail the centripetal force test, not just the bucket. Everything in the heavens, save one, spins or orbits with respect to the Earth, including the stars. Simple disproof of Mach's principle, or proof by contradiction. Assume the stars are inertial. The Earth rotating with respect to the absolute star frame is thus not inertial, which contradicts the assumption. And that's really important because we already established which frame makes the correct prediction for the rotational value. Putting it in the stars is just actually kind of physically meaningless because that's where the experiment isn't even taking place. So, in plain English here, the bucket proves that the lab frame is inertial. Anything spinning relative to the lab frame fails the same test because F equals mass times the angular acceleration squared times the radius, which gives zero force in any frame rotating with the lab frame. The stars spin relative to the lab frame. That is the diurnal sky that we see every night. So the stars would fail that test too. They are the rotating frame, just like the spinning bucket. The label fixed stars only means that the constellations don't shuffle relative to one another. It doesn't mean that the whole sky isn't moving relative to Earth. And a footnote on Mach, because Mach's principle is often brought up in these conversations. The popular paraphrase of his quote is that the distant stars determine the local inertial frame. And that's widely acknowledged on Wikipedia and in various textbooks, but it's very vague and it's not testable. Mach's actual quote was published. Uh, his actual published statement that you can look up is as Earth is in his quote. He says the rotation with respect to the Earth and the other celestial bodies is what he put forward for his Machian principle. The version that erases Earth in the textbook and paraphrases is not Mach. By including the Earth in his original statement, Mach is half right. The star frame on its own is invalid. All right, so the next example that we have relative to the old lab frame is Bennett's hiker. So a car accelerates at A down the road, and a hiker stands on the roadside. So the hiker lab frame analysis here for F equals ma all the way down to the Hamiltonian. So starting with the driver frame, the driver is experiencing a force that is the mass of the driver times the acceleration, and that's the real force that he feels as he's accelerating, as he's being pushed back into his seat. The hiker feels zero force because he's stationary with respect to the lab frame. The driver is in a non-inertial frame. The driver, if you were to try and make his frame equivalent, what would happen here? So the driver's uh, real force is felt here, and then the hiker that he sees, you would have to basically apply his acceleration to the hiker to make him go in the opposite direction and assume, if the driver is like, hey, well, I'm the stationary frame, maybe that hiker is moving away from me. This is what it would look like. It would create an acceleration in the opposite direction, away from the driver while he's stationary. Same goes with the momentum. The same situation follows. If there's no actual velocity, there's no momentum to be had there. So the hitchhiker doesn't have any momentum. Driver has the momentum. Doing it in reverse, is the outcome there to make the frames equivalent there. Same with the kinetic energy situation. The hiker is not moving. Same situation. Lagrange Hamiltonian again ends up being the same. So we're just going to run through the equations here, or run through the solutions here. So we got hiker. The hiker, the force on the hiker is 0. His momentum is also 0. Car plus driver equals force driver equals mass of the driver times the acceleration. Acceleration in this direction. All right, so when we get to lab frame analysis, the driver correctly predicts his velocity. The force felt relative to the lab frame. When we introduce the hiker, though, I'm sorry, yeah. So the driver also predicts the same thing in his inertial frame there. That's correct. But when you apply it to the hiker, like if you try to say that it's the hiker that's moving in that frame and that the driver is stationary, well, then you end up having to put the force in the negative so that it goes in the opposite direction there. Same situation for the momentum. It's a repeating thing. These two are kind of intertwined. Same with the kinetic energy potential. There's no height difference there, so there's no change there. But the hiker has to, have a force embedded on him to give him the movement required. So we see here a fictitious force coming in to make that frame equivalent there, and that's what it looks like when those are interjected to make the frames equivalent. And going on with the Hamiltonian with the momentum, we end up with the exact same scenario where the hiker doesn't have any velocity, so he doesn't have any momentum. So you have to introduce a fictitious velocity potential, which then can be extrapolated into his fictitious uh, force there. None of those give physically meaningful outcomes unless it's with respect to the lab frame, and to make the frames equivalent, or when you're dealing with a non-inertial frame, you have to introduce factors to make it appear equivalent. It's just like a math injection of it. So the takeaway: the V fictitious is not just unsourced; it has to point in the right direction. So this gets into in making the frames equivalent. Like, you have to know that with respect to the lab frame, that there's a correct way to interpret this. So you have to also make the direction go in the correct way. So that's kind of the summary of this, and it shows that in doing that, you're comparing it to the preferred frame, right? Like acting like the preferred frame is somewhere else other than Earth. We're always comparing these to the lab frame. Okay. So we're going to cover a simple. That was the hiker, and so now we're going to cover a simple pendulum. So this would be the classic, uh, like a just a regular old Newton pendulum, one that swings back and forth. So the mass of the bob is raised to the height h above the lowest point and is released at the bottom. At the bottom of the arc is going to be the velocity of the bob is equal to the square root of 2 times the gravity times the height that it started at. So we've got the analyses here for everything. So we'll read off a little bit of these as we get into a new scenario. So the tension and gravity are real forces at the bottom of the swing. So the tension is equal to the mass of the bob times gravity plus the mass of the bob times the velocity squared, the velocity of the bob squared, over the Lagrange times gravity plus the centripetal force. And that's a real source that's balanced and all that. So when it's coming to predicting that with the lab frame, you get the correct values there. Same situation with momentum. The bob's momentum oscillates from 0 at the extremum to the mass of the bob times the velocity at the bottom, and the changes come from real gravity and tension torques. Now, for the non-inertial frame, what we would be looking at, the bob would be at rest, and is the Earth is treated as the moving body of mass that moves at a constant velocity vb, where the acceleration of Earth is equal to 0. No source for any force. The setup is internally inconsistent. And then same for the momentum here. So Earth has the momentum of the mass of the Earth times the velocity of the plug bob in the frame, which has no mechanism for the source planet to scale momentum for the small plug bob. So obviously those values aren't what's measured. in that regard. So when we talked earlier about using the mass of Earth for the analysis and whatnot, that's what's coming from there. So same situation with kinetic energy potential. Doing it with respect to the lab frame, you end up with the correct values. When you do it with respect to the stationary pendulum and then having the Earth do the moving for it, you end up with insane values that don't make any sense. When you have the Lagrange situations, it ends up being the exact same thing because the mass of Earth has to be used uh, in the in the opposite frame. It ends up with a potential that doesn't make any physical sense. So like you can still calculate it out, but it just doesn't give a value that's physically represented in the lab frame. Otherwise, the pendulum would would just like swing to the moon essentially. Would swing off its little chain or rope or whatever. Um, so here, yeah, we're just looking at motion relative to the lab frame and the predictions of of the force that's created by that swing due to gravity and the centripetal force as it swings. So we get the correct prediction there. And the bob frame, where it's stationary and the Earth is moving, no force is produced on it. So it predicts that it's not going to be moving. The Earth is moving, and the bob is stationary. Same thing for the momentum, except here the momentum ends up being due to the mass of Earth. So it starts to show these like non-physically meaningful values here, where we get, uh, you know, all the way to e to the 25 there. All right. Same thing for kinetic, Euler, and the Hamiltonian here. It's, I mean, like we've seen the issue before. It's just kind of repeating the same thing at this point, and I don't want to like drone on and on. But again, when you're using uh, motion that isn't relative to the lab frame, you're ending up with these values that are non-physical, have no meaning. And you could distinguish correctly which is the correct frame to interpret it from based on the energy in the system. So, like, that when you drop that pendy, it's not flinging off into space or whatever. All right, so here's a really interesting one for Bennett's train. So here we're going to look at the difference between the classic and inertial frame. So what about, we've covered accelerations and rotations. What about something that's moving at a constant linear velocity? So here we have Bennett's train. A passenger on a moving train tosses a ball vertically at the speed v ball from the train floor. The train moves along the track at v train. So the analysis follows here. So the ball experiences real gravity. So force equals minus m times gravity times z, which would be its height. During the flight of the vertical motion, correctly predicted, the horizontal velocity of the train, excuse me, is carried by the train. No horizontal force in flight. The ball, and then in the train frame, which is non-inertial, the ball experiences only local gravity. The vertical motion is correctly predicted. The horizontal motion is zero in this frame because it hides the velocity because it's an inertial frame. It's traveling at a constant speed. So while you're in the train, you can't tell that it's moving. So only with respect to the lab frame do you get the correct horizontal velocity prediction uh, for that, and that's going to play into the energy predictions specifically because there's not going to be an effect felt, but there is a difference in energy summation here. So the ball's momentum here, again, it's lacking the horizontal component essentially, but it does make the correct vertical component. But the horizontal component is what is missing there. Same situation for the kinetic energy potential is where it ends up missing the 1/2 times the mass of the ball times the velocity of the train, and that would give them that horizontal component that isn't measured in the frame that's moving. Only with respect to the lab frame do you get the full correction. And the same situation props out for the Euler and the Hamiltonian. Um, so yeah, only when you have all the correct variables to insert do you get the correct answers. Now, if you don't have them and you don't enter them, the equation still closes, but it solves for the incorrect value. although you did, because you just didn't know that it was included or whatever, right? All right. Then, so to kind of look at what that looks like here, we're looking at lab frame and train frame, both correctly predicting what the ball is experiencing vertically. And then when we get into momentum, it's missing the horizontal momentum that comes out of the train. If you were to try and calculate it out, and the from the observer on the train, they would not be able to make the correct horizontal momentum prediction for the ball. Same for the kinetic energy. Only with respect to the lab frame do they get the correct horizontal full amount there. Without that, they're going to be lacking some energy to complete the full analysis. All right, and that pattern just kind of continues. There's nothing too crazy here, but what it shows is that even in a frame where you're moving at a constant velocity, there are ways that you can do an analysis to determine whether or not that frame is an inertial frame as defined by how we defined it or how it's defined in modernity. So we have Bennett's biker here. So this is another scenario that arose during a conversation. So imagine you have a cyclist who's has some mass and he's going to coast down a ramp that's at a height h, reaching a speed of v cyclist, and that's going to be equal to the square root 2 times gravity times the height at the bottom. So when we get into force analysis here, if you were to say that the biker is stationary and the earth is rising up uh, to like give the biker the appearance that he's going down the ramp, well, the force that's going to be produced from that when you use earth's mass is going to send the biker going off at some crazy speed. Whereas when you do it with respect to the lab frame, the biker is moving, when it's done with the biker's mass with respect to the lab, you get the correct force applied. Same for the momentum situation. You get an absurd amount of momentum if you try to use the earth frame. Same for kinetic and energy potential predictions here. They get inflated to the planetary scale, which isn't what's measured. Like the guy, no one's ever gone down a ramp and shot off into, you know, just whatever. Same for the Euler and Lagrangians there. You can solve them. You don't have to make any fictitious predictions or anything or corrections or anything like that. But you'll get the wrong value if you don't make it with respect to the lab frame. If you try to use the other frame, you will get the astronomical planetary values that don't make any sense. Okay, and that was for Bennett's biker. And the same pattern is going to follow across the pendulum for a Foucault pendulum at its turnaround point. So that we're going to make some similar predictions, but at the point where the pendulum is stationary, when it's going to go to its swing back, it predicts that it has, not moving. So it's stationary with respect to the lab frame. So it predicts zero energy potential, and all of that. So we'll get into that analysis as we continue. So here is I think this one is for the bike here. So we're about to wrap up on the bike. So here's the figures for that come out of it. So bike frame, correct value, biker stationary, incorrect value. When we get into momentum, correct value when you use the biker, when you use the planet, or when you use the planet to do the work, you get the astronomical value that makes no sense. And that same pattern continues for kinetic energy, the Euler-Lagrange, and Hamiltonian. All the way through, nothing too fancy in any of these either. And now we'll get into the Foucault pendy. So a long pendulum is suspended in the laboratory and has a plane of oscillation that rotates relative to the laboratory floor at a steady rate, where we have derivative of the angle over time over the derivative of time is equal to the sidereal rotation times the sine of the latitude. Yeah. Yep. Sidereal velocity of the celestial sphere. So yeah. So for us, it would be celestial sphere. For globe lad enthusiast, it would be the rotation of Earth. The rotation completes per 24 sidereal hours, and at the poles, not at the equator. Okay. So the only thing different really that we do here, so the globe the non-inertial globe would introduce this Coriolis force here, we introduce a coupling force relative to a rotating medium. So instead of using the Coriolis force as like its as like a counterpart to the rotation force of Earth when you're traveling perpendicular to it, this would be traveling perpendicular to the angular rotation of the medium. You're going to experience, like the same kind of you can think of it as the same kind of Coriolis force that's going to be attributed to it. So there's no the only values here are like angular rotation. Uh, there's no mass or anything like that. All that comes out of that is just the angular rotation. Okay. So for the momentum, so anyway, yeah, it's going to predict the same precession stuff, and we'll go over that as we continue. But for the momentum of the Bob's momentum is reoriented, the magnitude preserved by the perpendicular medium force. Uh, Real reaction is on the rotating medium, negligible recoil because the medium's moment of inertia is the entire celestial sphere. And of course, the globe lads, they're like the rotating non-inertial globe frame would be the Bob's pendulum changes due to the fictitious Coriolis with with no real reaction partner, which isn't true. I need to change that. Their reaction partner would be the rotation of Earth. It would be like the same way that we're using the rotation of the medium, so that's actually incorrect. Um, so in this regard, same prediction here. But as we continue on, we'll see the differences when we get to the figures. Um, so for energy potential here, this is where we get into the situation with the swing back for the analysis. We're gonna get different values here as we continue. Um, so again, there was nothing too crazy in there. It was just introducing that coupling term for for there to be like a counterforce to the rotation, the same way that the Coriolis force is that counter term when you're traveling perpendicular to it. And then the Hamiltonian, all that is conserved. So we'll get into the figures now. This is a quick note on using the medium as the rotational vector. So it's just under the same kind of principles that would be done for electromagnetic coupling, where the was it charge or times the velocity times the cross product of the magnetic potential vector, magnetic vector potential. Yeah. So anyway, same situation here, and that's just going to create that cross force when traveling perpendicular to it, the same way that it would be predicted there for electromagnetes. Um, what we can go over here now is the math analysis here. So for the most part, like I said, we make the same predictions, except for when we get to. So I'm just going to breeze over these. So except for the term here, when we get to the turnaround point, when it's stationary with respect to the lab frame, when it predicts zero motion. Now, if the Earth is rotating and it's causing that bob to swing, then it's not truly stationary. There's going to be 1.3 joules uh, megajoules there of uh, of kinetic energy that's never measured. So you could, get a thermal camera out, see if you could measure some sort of heat change or something like that. But this is never experienced, never measured, never harnessed, doesn't exist. And that's what comes out of using the fictitious frames for the analysis. The only frame that makes the correct prediction every single time here is with respect to the lab frame for all cases of dynamic analysis. And then there's a quick summary down here where we have a summary matrix of the mathematical predictions. And we just went through them all, but I'll leave them up here. And then let's see. So in short, the lab frame is able to make all the correct predictions, and you have to introduce fictitious terms to satisfy the Earth as a non-inertial frame. And in doing that, you end up getting predictions where you have energy where there isn't any, and you're not satisfying conservation laws, whatnot, correctly. You would end up with like astronomical amounts of energy and stuff that aren't measured. And our assertion is that the lab frame is the frame that is stationary. Uh, Dr. Bennett, if you're there, would you like to add anything before we open the floor to questions?
I think Dazzle was disagreeing with your terminology of which Earth-sided Earth frame you were referring to during your presentation.
Cool, we can get to that.
Yeah, he had some ECI, ECEF differentiation questions, I think.
Yeah, I've got a couple of questions. Because in an inertial frame, we shouldn't have to apply fictitious forces, right? A projectile motion should be something that we can simply apply the basic Newtonian physics to without any fictitious forces whatsoever.
Sure.
Main question I have is, if you lift and shift the lab frame to Mars, what happens to this magic vorticity that you need to make everything work on Mars?
Mars is moving relative to the lab frame. Same situation as the star frame. Moving to a different location doesn't solve anything.
But the physics on Mars, you could apply the same logic you have here to using Earth as the reference frame. It would work just as well on Mars.
Incorrect. Mars is moving relative to the lab frame.
I think you'd find, Alan, in practice that you would get exactly the same results on Mars as you do on Earth.
Yeah, how do you know that?
I think you should show the math for that. That would be great.
Standard physics will show you the maths.
Yeah, so what we're going to do is we're going to attach a velocity vector to all the things that we're doing for solving in the Mars frame, because Mars is moving relative to the lab frame, and it's going to make the incorrect predictions every time. So, no. Incorrect.
You could solve everything on Mars just as you've done on Earth here. You don't need to know about Mars when you're solving for Earth, right, in your scenario. So if we're on Mars, we also don't have to care about where Earth is. Earth is not important if we use Mars as our lab frame.
Incorrect. If you move to the Mars frame, then Earth would be moving relative to Mars, and that would contradict the already established bucket experiment. So you can't do that.
The bucket works on Mars.
Same situation.
You'll get the same result with a bucket on Mars as you do on Earth.
No, the Earth would be moving relative to Mars in the Mars frame. You would get the incorrect result. It would be a contradiction. You don't just get to move the frame, have it be stationary, and then have everything else also be stationary. Everything would have to be moving relative to it.
I'm not talking about a bucket on Earth.
I know what you're talking about. I just went out. Okay, can you repeat what I just? Can you do you understand what I just said about how the Earth would be moving relative to Mars, and that would contradict the already established lab frame stationary, making the correct prediction for the bucket?
That's what I'm trying to say.
Did you get any of that? Did you get any of it?
Mars is equally as valid to set up this fictitious lab frame as anywhere else. You will get the same results. You can draw the same conclusions.
Yeah, but he's saying, what are the consequences of doing that, though?
And also, there's no observer on Mars doing that. That's never been done. You're invoking a hypothetical fictitious to try and falsify the lab frame. The lab frame was falsified by contradiction, showing that it makes the incorrect prediction. So where are you going with this, Slick?
That's not falsifying the null, Dazzle. Your hypotheticals don't falsify the null.
I'm not caring about falsifying the null.
I know, that's why.
Oh, well, okay. Well, hold on one second, though, because this is extremely important, Dazzle. This isn't the show up and just talk endlessly and confuse everyone so that there's no resolution. If you're not here to falsify the null, you're not here to contribute anything of value. So your answer was answered.
Why the Earth is being chosen?
Your question was answered, and we went over why it's being chosen, because all the laws of physics apply to it. If you try to do the reverse and have the another frame be stationary, then the Earth be moving relative to it, you would then contradict all the already established results.
Okay, so Are you saying that we can't predict the motion of something on Earth from a Mars-based reference frame? Why does
I'm
Earth even
saying
have to be involved?
let's pretend that the train is Mars and Earth is stationary. The same
Train on
velocity
Mars.
situation, same the same situation is going to lead to the incorrect result. It's moving relative to the lab frame. If you're on the frame and you think it's inertial and you don't know that, you're not gonna account for the velocity potential. So you're gonna have the wrong horizontal velocity components.
I think you might be
And you're gonna
misinterpreting
and on top of that, 1 second, you're going to contradict what was already established in the lab frame. If the lab frame makes the correct prediction and it's true for stationary, then you can't move to another frame, then have the lab frame be moving relative to that, and then still say that those are still valid. But like that doesn't even make any sense, dude.
So I
So
think you might be
your objective
misinterpreting what
here is
I'm
to
saying.
falsify the null. Nope.
I'm saying that
Consider the null.
we can choose Mars as our lab frame and apply the same logic and get the same results.
Okay. You can't, and I just showed that with a train, a pendulum, a hiker, a
No.
fucking guy in a boat. Like, dude,
So
no.
Alan,
And Daza, show where the lab frame makes the incorrect prediction. Other than that, there's nothing really to discuss here.
I've got to run anyway, but I might be able to come back in a few minutes.
Bated breath, Deza.
Yeah. Oh, yes. The material will be posted here. 1 second. Sorry about that. I totally forgot to link that at the beginning. Uploading it to GitHub right now. And I'll get you a link for that. All right. Any luck on the mic casts? No luck as of yet. Did anyone, in the meantime, did anyone else have any questions or comments about the...
I mean, essentially, from what I can gather from this, Alan, is you're kind of like for example, in the train example, you're just kind of describing like what's described in the Oberth effect, right?
I don't know what that is.
The Oberth effect is the fact that if you take the velocity of something relative to something else, you have to take into account the increase. Like, for example, in the Oberth effect, when it comes to rocket propulsion of your reaction mass, you get more total energy out of your expulsion of your reaction mass when the rocket is moving faster relative to some background frame. Like in the case of the Earth, like in a rocket, if you want to boost a rocket's total energy, you would burn your engine at periapsis when the rocket is moving its fastest, because then you're going to get the most energy out of your reaction mass, as opposed
See,
to
when
if
it's
you if
moving
you if
fastest
you if you
relative to to a fixed like location. Yeah, that
right
sounds very similar.
well,
Yeah,
which is like the lab. In your case, that would be the lab frame.
sounds very similar. Yeah. See if that link's available yet. All right, all the links for everything is in there. So the Jupyter Notebook link is in there, and then there's 2 PDFs. One has the math stuff included from the code, and then the other one has just just like the summaries or the results or what have you of it. So it's a little shorter read or whatever. That should be everything. So if anyone wants to review that, check the math, I got something wrong, so on and so forth. Happy for corrections and whatnot. Just let me know. And then some of this kind of bleeds into another project that I'm doing, but the analysis of what we went over tonight starts explicitly here on section 2 and ends down here at section 3. I'm going to guess if I was a betting man. Yeah, section 3 here. So yeah, section 2 is the relevant section for tonight. The other stuff is still in formulation or whatever. This is like a rough working draft. But this section is should be pretty solid.
Hi, so where can we review the draft?
Yes, sir. The link is in the live stream main chat at 19:03 past the hour.
Can't wait to go back and listen to this one, Alan. Of course, I think it's on topic for, is it planes landing on Earth that you're talking about tonight? I'm just coming in at the end here. Okay, yeah, that's my thing. Right on. Yeah, did the null hypothesis I sent you help at all for the presentation, or did you just do everything separately from what I sent you?
Oh yeah. All of this was done before that, but your thing will be a separate thing for planes. Like I'll help you make it.
Oh, okay, cool. Yeah, right on. This wasn't particularly just about planes. It was more about the atmosphere turning with the Earth or Coriolis, or what was it?
No, this was about dynamic analysis and future predictions of motion based on the lab frame versus non-inertial frames and what it looks like when when like fictitious forces are injected into the equations and whatnot, and what the results end up being. And Cass said the scientific method requires a repeat of Newton's bucket on Mars. When was this done? And he said he gets he said, I get stream lost when the voice is attempted. Let's see. So maybe my stream is too powerful. Let me try and use it. Let me just turn that off real quick.
That's good. To falsify the null, we would need your Mars Newton's bucket example. Otherwise, it's hypothetical nonsense and garbage.
All you have to do is just go to Mars and do the bucket test there.
No, all you can do is allow me the possibility to go to Mars.
Yeah, in like 2040, I'm sure we can do that. Where's the link to the document? Right here, sir. I'll send it again.
Didn't they send up another rover with a bucket? I thought they sent a bucket last time with that rover.
ZZ Pop. There you go.
All right, thank you. There we go.
Yeah, it seems like the ball side's happy to talk about.
Go ahead. Does Cass need verified to talk or anything? Or no, he has server access.
Yeah, we were calling it Coriolis Week last week. I guess Jeremy started calling it that, and then I just started with calling the stuff I recorded as Coriolis Month, because last time we tried to do a Coriolis Week, it ended up going on a month anyway. So this is a good timing for this inertial, non-inertial frame business to be talked about, because that's what it's about. They're happy to talk about. Go ahead.
Oh, I was gonna say I got a really good counter example for Coriolis force. So there was that guy that did that long distance shot that was like 4 point something miles about 4 or 5 years back now. And that gentleman did that. Jaron emailed him because all the websites and blogs and whatnot were all saying, they all said the same thing. They were like, and it wouldn't have been possible unless he calculated for Coriolis, yada yada. So Jaron emailed him and was like, hey, did you account for Coriolis? And he said no. And he replied back and was like, no, and I'm not a flat earther, but at these distances, accounting for Coriolis would be like somebody who weighs 600 pounds trying to buy thinner inner tubes to get an advantage in a cycling race, so so it would be like a non-existent thing. And then so I was talking to another globe lad who's pretty up to snuff on the physics, and he said that it would be great proof for the globe if that gentleman had to shoot east to west to quote unquote not account for Coriolis, because if you're shooting with the direction or against the direction of rotation, you're not going to experience any Coriolis. Coriolis is a force that's felt when you're traveling perpendicular to the plane of rotation. So if he's shooting in any other direction that isn't east to west, that would be good evidence that the Earth is stationary. So I was like, okay, cool. Let me see. I'll tell Jared, and then he can email him back and see what he says. So Jaron emailed him, and in the time where he was waiting for the email to come back, I was looking at the website again, and I saw in the record shot where they're standing by the target, you can see the moon in the frame. So we know the time that the shot was. So I just looked at where the moon was in that time and got the direction of it, and found that he was shooting south by southwest. So literally shooting kind of diagonal to being perpendicular to that Coriolis force. So it would definitely be subject to it. And he ended up emailing Jaron back and saying, hey, don't tell anyone this, but the direction was south by southwest. And he never specified why not to tell anyone anything. But I would assume that he knew the implication of the Coriolis situation, because that's what my buddy came up with, who was into the globe stuff, and was like, the implication would be yada yada yada. So I think that's what. So anyway, I thought that was interesting that he said that. But yeah, he did not account for any Coriolis, and we have all of that documented, on record or whatever, so that can be pulled up.
Yeah, I remember back when that was going on, when you were talking about Jaron finding having that exchange back in the day when that happened. It's interesting. West southwest is what I always talk about, because that's the real gotcha. Because I mean, there's a whole conflation, of course, going on, it seems, with the Coriolis, end quotes, and the Sagnac effect, or whatever that 15-degree drift is that they're detecting with their instruments. And that's just like secondary to the whole idea that we're talking about 1,000 miles an hour at the equator. If you're going west southwest from a lower latitude, it's going to increase the speed, but then you're also going against the spin. So the variables are just incalculatable as far as how the plane or anything would be in sync at that latitude where it's now 1,000 miles an hour instead of 0 up to 500 or whatever latitude the conserved momentum is said to be. But yeah, when you're talking about trajectories of the sorts, even with bullets, you're gonna have wind factors or spin factors from the barrel of the gun and all these things that are factored in. And in fact, I agree that whatever this Coriolis effect would be, you could just chalk it up to all kinds of other things, and that's why they put it in the equations. But it's always like canceled out to be close enough to 0. But they can say they factored it in because there's wind and all these other things that might be more affecting whatever the projectile is experiencing anyway. So when I did that song, that Hidden in the Winds, I mean, it would be hidden in the winds if it even existed, but that's the perfect excuse to say it exists, but you can't detect it because the winds would be more powerful. But that's the whole thing, is that if you're just talking about the 15-degree gradual difference, then you might have a point. But when you're talking about 1,000-mile-an-hour jet with 40,000 pounds of thrust resistance that can go all over the place, if there's any point at all where the ground is moving eastward tangentially at a different rate than the jet, all you'd have to do is have cameras all over the bottom of that jet and show that the Earth is actually rotating east to west or west to east underneath at any point. And you could have
Yeah.
like sensors and cameras
Yeah,
showing
Dave.
that the plane's going this way and the rotation's
Dave,
going this way.
this isn't necessarily related to the presentation here.
Oh, I know. I'm sorry.
Yeah, you're good.
I didn't hear the
You're
presentation.
good.
I assumed it was about, inertial, non-inertial reference
Oh,
frames.
man,
I assumed that was
Dave,
right.
Come on.
No, it wasn't. I told you what it was about, and then you talked about planes for a while.
Wait, you said it. You were talking about the lab frame and the atmosphere, or what was it? I'm
Nope,
sorry. I
never said
totally missed the
that.
presentation.
It's all good. Does anyone have
Sorry
any
about that.
questions? It's okay.
Yeah, I had a question. So I'm reviewing over the hiker example, and I
Mhm.
want to make sure I understand it. The hiker isn't hiking; they're staying stationary on the Earth as the car goes
Yeah.
by, and then we
Yes, sir.
switch to the car's frame of reference.
hmm
Okay, and then we reanalyze the motion of everything from the car's frame of reference.
Yes, sir.
Okay.
And it's like that for pretty much every single scenario.
And is the point that the world looks very different from the stationary versus the accelerating reference frame?
Yeah, the point is, as you go through all of these, is that even by the modern definition of an inertial frame being moving at a constant velocity and them all being equivalent, and you can't really tell, and so on and so forth. Well, the point here is that you can tell, and we show that through the dynamic analysis, showing how different energy predictions either fail or conservation, makes the wrong prediction, so on and so forth. So we give a method here to differentiate between an inertial frame as defined in modernity, moving at a constant velocity, or an inertial frame as being truly fixed and stationary.
But in the hiker example, you're not looking at a constant velocity car, you're looking at an accelerating car, correct?
Correct, but we go through all examples. There's a train scenario where it's moving at a constant velocity and it has an observer in it who would be
Okay,
considered an
which
inertial
one's the train
observer.
scenario then?
I believe it's right under the one you're looking at now, or just keep scrolling down. You'll get to it. It's one of those next upcomers.
So it's after the car one.
Yeah, but it's called Bennett's train if you need to control F it.
So a ball is dropped on the train. Do I have that right?
A gentleman throws the ball up in the air.
Okay, so someone throws the ball up in the air and then it falls back down. And they see it go up and down, but to the outside perspective, it goes up and down as the train moves forward.
Correct. And so
Okay.
when you get into when you get into what's the horizontal kinetic energy, so on and so forth, or the horizontal momentum component, etc. If you're on the train and you don't know that you're moving, you consider yourself inertial, you're going to make the wrong horizontal velocity component prediction. Essentially, is what that one shows.
Well, yes, yeah. So in the two perspectives, in one perspective, the ball has no horizontal velocity. In the other perspective, it does have horizontal velocity. So there's a massive disagreement about the horizontal kinetic energy of the ball. Do I have
Sir,
that right? Okay. Um, okay, now I'm just reading through this. I came in late quickly, so I don't mean to ask something that
you're perfectly fine.
is obtuse to what this is, but my next question is, and what's the problem with that? What's the problem with these two perspectives having a disagreement about what the total kinetic energy of the ball is?
Well, it's asserted that all inertial frames are equivalent, like number one, and we can show here through dynamic analysis that that's not true. So it's about differentiating between a true inertial frame versus one that is like semi-inertial sometimes when it needs to be in this scenario versus another scenario. so on and so forth, we provide a consistent methodology for dynamic predictions using a stationary Earth as being truly fixed.
Isn't the dynamic prediction the same? The ball goes up and then comes down. I mean, the only thing that's different is the horizontal component of velocity, but that's not dynamic. That's constant because the train's moving at constant velocity.
Well, that's just one of many of the contradictions that was shown. So in the pendulum scenario, where the pendulum is on the swing back when it's stationary with respect to the lab frame, if the Earth were truly the cause of the precession of it, then it would actually still be moving at 300 meters per second at that
Well,
location.
that's an accelerating system as well, the pendulum. That's why I'm particularly interested in the train scenario, because it seems to be the one scenario that's constant velocity rather than going from stationary to dynamically accelerating.
Well, in every scenario, you see through the dynamic analysis where there's contradictions in the predictions. And here, the contradiction would be in the horizontal component. You ask if it's important, and I would say yes. And
I don't
consistency
see.
is
I don't
important.
understand why you're saying contradiction though. Like in one frame of reference, the ball has horizontal velocity and horizontal kinetic energy. In another frame of reference, it doesn't. I mean, does the word difference mean contradiction here?
Well, only one frame correctly predicts the total amount of energy, and it's with respect to the lab frame. So when you would what you would have to do to falsify our null hypothesis is show where the incorrect prediction is made with respect to the lab frame for any of the dynamic equations that were used. So there's
What do you mean the
5
correct
there.
energy? I mean, if you say the lab frame is the correct energy a priori, and then you say, okay, from the frame on the train, you don't see the horizontal component of velocity, then you've sort of just worked in what your conclusion was there.
Well, we compare it against a multitude of frames, and our conclusion is the only one that satisfies all the conditions dynamically with no fictitious terms or terms that lead to physically meaningless results.
Well, there's no
So our
fictitious
conclusion
terms on the train
so so
scenario, though.
so what's that? There's no fictitious terms on the train scenario. No, but
Yeah.
it leads to but it leads to the incorrect energy predictions. So that's one of
What do you
the
mean
parts of
incorrect energy
dynamics.
prediction?
It
How
has
could an
no
energy?
horizontal it has no horizontal velocity component to it.
So
So
how are you
it has
establishing which one is correct?
because the train's moving relative to the lab frame, therefore, if the dude is on the train and throws the ball, it has a horizontal component to it. You only know that from comparing it with respect to the lab frame. Comparing it with respect to the train frame, you would have no horizontal component. You'd be missing the kinetic energy potential there and also the momentum there.
It feels very cyclic. What I'm asking is, how did you establish that the lab frame compared to the train frame was the preferable frame in the first place?
From your perspective in the inertial frame of the train, what's your velocity? Zero.
Yeah. And I'm asking what's wrong with that? What's wrong with the person on the train saying that they're stationary?
It leads to the incorrect energy prediction with respect to the lab frame, with respect to their actual velocity.
Well, it leads to a different prediction, yeah. The two frames of reference have a disagreement.
Not just a different prediction, but the correct prediction. The total full amount is predicted from with respect to the lab frame. Extremely important.
I, I mean, you're saying that the lab frame is the correct frame because you're saying that the energy the lab frame measures is the correct energy because it's the energy as measured in the lab frame. Like,
And as measured in a frame moving relative to the lab frame, you get the incorrect prediction.
and
Therefore,
you know, it's
our definition of an inertial frame is defined by the results of these experiments. Like the circularity that you're trying to assert actually is reversed. It comes from saying that you can't tell and there's no way to tell. Well, how'd you tell that? Well, you told it from trying to do it from the train of the frame. When you compare it to the lab frame, the correct predictions made. The results you're looking at are a consequence of the comparison, not a circularity. right? The correct energy prediction is the correct energy prediction because the frame's actually moving and has a horizontal component that's real. It has a real horizontal momentum component to it. So not accounting for it is it's not correct.
So it's not the train frame is not correct because the train frame does not account for the horizontal velocity of the train as seen from the lab frame, which is correct because the lab frame is correct.
It's not correct because the lab frame is correct. It's because that the motion relative to the lab frame allows you to calculate all of the motion that's relative to the lab frame. Relative to the frame that you're using that's in motion, that's not a real inertial frame, you get the incorrect prediction. That's why it's incorrect. The lab frame isn't correct because it's correct. It's correct because you get the correct value of what the ball is actually experiencing. What the correct value is independent of the lab frame. We're comparing to the lab frame, and that's the one that matches. When we compare it to the train frame, it does not match. It's not a circular comparison. That's a mutually exclusive outcome. For some reason, this guy is muted.
Oh, you mean he deafened right in the middle of the discussion?
Yes.
Yeah. Maybe he had a phone call or something.
Mm.
Right when you just said the key point that he would have to respond to if he understood what you just said.
Isn't there an issue with using like two competing frames of reference? Because you could just be selective about whatever bias or preference you have. You know, like I can just go to this frame of reference because the other one doesn't, comport what I want.
So they often talk about So they often talk in physics like you can use any frame you can use any frame arbitrarily, and then you can just one second, Z-Pop. They say like you can use any frame
Testing.
arbitrarily, but then we can hear you. Can you hear
Oh,
us?
sorry, cut out. Wi-Fi died for a sec.
No worries, lad.
I am sorry that I cut out mid-sentence.
Yeah, if you guys want to continue your discussion, I could ask you later on.
No. I cut out and you were answering your question. Go ahead.
No, it's fine. We can come back to his. So to get back to you real quick though, the lab frame making the correct prediction isn't circular. It's a mutually exclusive outcome that we make the correct prediction. We're comparing it to other so-called inertial frames, and it's not making the total actual prediction for momentum or kinetic energy potential. It's not circular. It's a mutually exclusive outcome.
Let me back up for a sec. Is it your understanding that all inertial frames are supposed to agree about the amount of kinetic energy that something has?
It is stated that in an inertial frame, you cannot distinguish it from any other inertial frame. And I'm showing here a very clear way to show the distinction using dynamic analysis.
Okay. So the statement is not that all inertial frames will come to the same conclusion about the specific value of energy or momentum something has, but that all inertial frames need to come to the same conclusion about the process of force, acceleration, and conservation laws. Like, for example, if something starts with an energy of 100 and goes up to an energy of 150, the change was 50. Now, from another perspective, it might have started at an energy of 25 and gone up to 75. And what the frames are agreeing on is the change, the amount of energy being changed hands, not necessarily what the starting baseline was.
Yeah, so that's a different hypothesis, number one, right? So the objective here is to show where the lab frame makes the incorrect prediction. So when we do it with respect to the lab frame and we account for the total horizontal component in the inertial frame for the observer on the train, through that analysis, we get the full correct amount. When you do it from the train, you don't get that amount. And that's to say that, like, saying that pretending that amount doesn't exist because it's not relevant in that frame for that particular moment isn't part of the analysis. We're showing that even in a so-called inertial frame, there is a dynamic analysis that's being shown here that falsifies your position that all the frames are equivalent. To say that they don't have to converge to the same results is retarded, because they have to. Otherwise, they would lead to dynamic contradictions. So if they don't all lead to the same conclusion, then they're not all equal. And if they're not all equal, like what we're showing here, is that the lab frame is the one frame that actually makes the correct predictions for the total amounts for everything, with no contradiction, no missing terms, no missing components. You can't do that with any other frame. As you just said, when you do it to two relative frames moving to one another, you get that relative difference. This is the full absolute total amounts, only with respect to the lab frame every single time.
Dynamic means change. Saying that two things have to agree on the dynamics means they have to agree on the amount of changes that took place. They have to agree on any amount of energy or momentum increase or decrease. And what I'm saying is, what's the issue with saying the two different frames had a disagreement in what the starting value of energy is if they agree on how much energy increase or decrease took place? They're still looking at the same dynamics. They're still looking at the same quantities of energy that have exchanged hands between objects that have gone up or down. They're disagreeing on what the starting amount of energy was within the total system. But that's a constant.
I've said it.
That's not part of the dynamics.
I've said it several times, and then you've restated the same question. Can you repeat what my answer was?
Well, you seem to think that a constant amount of energy is part of the dynamics of a system. And what I'm saying is that the dynamics of a system is the process of energy going up or down, the amount to which it has increased or decreased, not what a starting value of energy was that it might have had.
No, you're incorrect. This is the total amount of energy that's present in the system with respect to the lab frame. It has nothing to do with what you said and trying to analyze it at different states. That's what you're trying to do with relative motion.
No, what I'm just saying is that the word dynamics does not make reference to the total energy of a system.
Buddy, when I say dynamics, I'm talking about future predictions of motion based on causal mechanisms. So force, energy predictions, all of these equations here are for dynamics, for mechanics. So if these equations are not in agreement, then we can distinguish between frames. So what you're saying is it doesn't matter. What I'm saying is I can clearly distinguish frames, and you're not really saying a difference here. You're just asking, why is it important?
Of course,
I'm distinguishing between frames.
Of course, you can distinguish frames.
So not all inertial frames are equal. There is one superior inertial frame, and that is the lab frame, as shown here by dynamic analysis.
I am saying that all inertial frames are equal in the very specific sense of agreeing on changes of energy and agreeing on how much energy an object has gained or lost within some sort of dynamical process. If your claim is that it's also important for all frames of reference to agree on what the total energy is, then that's certainly something very new to me that I've not heard before. I've only ever heard that
I'm saying you can distinguish between inertial frames.
Yeah.
There is a preferred frame. So your take is not what the mainstream take is. The mainstream take is that all inertial frames are equal and that you cannot differentiate between them.
The mainstream take does not say that if I'm riding on a train, I don't know that I'm on a train. The mainstream take
that's exactly
does not
what
say
it
that
says.
we cannot.
That's it. But that's exactly what it says. We're on the Earth, but we're traveling around the sun at 30 kilometers a second, but we're in a closed system, and the velocity isn't changing very much, so we don't know that we don't feel that we don't know that. That's exactly what they say. You're literally in contradiction to what the mainstream says due to some, I don't know, personal philosophy or something. But what you're agreeing to is falsifying the mainstream position there. So yeah, it is. And real quick. Now, keep in mind, lads, the purpose here is to falsify the null hypothesis. Asking why it's important or not showing how the lab frame is making the incorrect prediction does not falsify anything at all about the null hypothesis. And showing that the lab frame is a unique frame for dynamic predictions.
The mainstream stance is that if I'm on a train moving at constant velocity, not accelerating but constant velocity, and I throw up a ball and catch it, I can't tell from that experiment if I'm on a constant moving train or a stationary train. What you're saying now is that if I'm on a train that is moving and I look out the window and see that the ground is rushing by, that I know I'm moving with respect to the ground, which, of course,
Absolutely. That's absolutely not what I'm saying. Hold on. Let me stop you right there. That's absolutely not what I'm saying. I'm saying that from the lab frame, you get the total horizontal component of based on the velocity of the train moving relative to the lab frame. Looking out the window has nothing to do with what I said. We're doing dynamic analysis. Okay. So your job here is to show that the lab frame is somehow making the incorrect prediction, or that somehow that your train frame can somehow self-satisfy the horizontal velocity component without knowing that you're moving. That's the task at hand.
Of course, if the lab frame sees the train going by, they see it going by with a higher kinetic energy than someone sitting on the train who sees this train as stationary.
So the lab frame makes the correct energy prediction for the system, whereas if you do it from another frame that's moving,
what I'm saying.
Okay. No. When you say a different one, though, are there any other momentum variables to calculate for horizontal momentum? Is there any other additional thing to add from the that's moving relative to the lab frame that could be added? So when I say the correct one, I mean the total amount based on the only parameters that are available to do the analysis with.
I just
so
don't
it is the
understand
correct
word
one.
correct.
It's the only one that's available when you correctly account for all the horizontal and vertical components of the system. When you account for everything that's possible relative to the lab frame for the motion. That's what makes it correct. There's nothing else to add to it. It's not missing a component. So if we do it from the train frame, it's missing the horizontal component. So it is not fully complete. Okay. I'm not saying that there's not a difference between them. That's my point. But the only one that makes the full total value prediction is when it's with respect to the lab frame.
I think this is just a misrepresentation of what the mainstream statement is. I mean, no one has any issue with saying that the total kinetic energy of an object will look different in different frames of reference.
Well, great. Then the Earth is stationary then.
Yeah, you can take the frame of reference where it's stationary, right? The question is not
I will,
if
and I showed I will, and
like,
not only did I
look
do
different,
that, but I showed that future predictions of motion based off of that stationary this are the only ones that make the correct prediction. That is my premise. That is what I'm doing.
Somebody
That is
sitting
what
on
you
the
have
train
conceded
can
to.
correctly predict how long the ball will be in the air before it falls down. Like if I throw a ball, if I'm sitting on the train and I throw the ball up and predict how
not
long
in
it'll take before
disagreement.
the ball lands in my hand again, I can do that correctly.
That's section one. That's section one. That's not what's in contention. The horizontal velocity component is what's missing from the analysis. We make the same prediction we make the same
measure the
prediction
train's
for that.
horizontal velocity on the train. I'd need to be off the train to measure its horizontal velocity as it goes by.
I agree. I agree. So perhaps read through the full doc and we'll come back to this. But as of right now, nothing has been shown that the lab frame is making the incorrect prediction or that any other frame is making the equivalent prediction that satisfies all of these that we use. So remember, we use force analysis, momentum analysis, energy prediction, a Euler-Lagrange, and a Hamiltonian. So we did energy over time of the system and conservation of momentum of the system.
So when do you plan submitting this for publication? This is radical stuff.
Yeah. So when you say stuff like, when do you plan on submitting this to, what's it called? I turn your volume down to 0.
Of course you did, because you
when
realized.
Do you plan on showing that the lab frame makes the incorrect prediction?
So when you're going to?
It's not
radical. Did you turn me down?
Did
this coward turn me down? Did this coward really turn me down after one
you're
comment?
Talking to someone who's actually not.
Did this coward?
Not.
I would.
Yeah, it's best to just not even engage with that guy. So go ahead and finish your thoughts, Z-Pop.
No, I think So the thing I'm finding circular about it is I understand that you think that there is one true frame and other frames of constant velocity to it are incorrect. But what I'm trying to say is that if you already think that velocity is relative, that there is no true answer to what an object's velocity is, that that is perspective dependent, then it follows immediately that the total kinetic energy is also perspective dependent. Like, it is not like the fact that the mainstream framework of physics is that it is okay to say that velocity is relative to one's perspective. It goes with that the momentum is also relative to one's perspective, that the kinetic energy is also relative to one's perspective. So that's why I say I'm not really seeing the contradiction here.
That's what's circular. What I'm showing you is that dynamically they are not equivalent, and you could see the difference between them. And you also agreed to that.
But
So you're
constant
holding like
velocity
this
doesn't
weird.
mean dynamics.
So you're holding.
Like,
you're trying to hold this. Dude, we're doing an energy prediction of a change in energy over time of the system and change in position. Like that's literally.
but that's the same.
These are
Wait, the change in energy.
these are these are dynamic. These are the equations. Like you're saying, you're like bro, like listen. The important factor here is that the lab frame makes the correct and total amount of the prediction every time. It doesn't require fictitious terms. It doesn't lead to physically meaningless answers.
There's
Any
no
other
fictitious
frame,
term on the train.
any other frame is listen. That this doesn't just apply just to one scenario. There's like 6 that I gave.
I'm just trying to understand what I'm supposed to take away from this one scenario, from the train scenario. And maybe that's not the more interesting scenario.
The takeaway from the train scenario is that even in an inertial frame as defined by mainstream, it leads to the incorrect prediction. And that only one frame consistently makes the correct prediction for energy of the system. Now you say, oh, well, it logically follows that if you're at a constant velocity, then your da-da-da would also be at a constant velocity. That doesn't logically follow, because you not knowing about the momentum doesn't change the fact that there's a horizontal momentum component. That's the point. That's the point of this, is that you can't falsify the lab frame by showing that it's making the wrong prediction, or that it makes a or that another frame satisfies the prediction for every task. So for every single one of these analyses are all independent of one another. They all make different predictions for what it should be. And only one frame is satisfying it every single time. That's the point.
I mean, you've got these equations written right here in front of us to look at. Momentum is mass times velocity. Kinetic energy is 1/2 mass times velocity squared. So if the velocity is different between different frames, then the momentum is different between different frames, and the kinetic energy is different between different frames. I'm failing to see why you
with
feel
respect
it's
to which frame,
different.
and with respect to which frame, it makes the correct prediction.
What do you mean by correct? I don't understand what you mean by correct.
Well, I defined it several times now, and I'd like you to repeat my answer.
On the train example, like what do you mean by the correct energy?
I've said it several times now.
The lab frame. You mean the lab frame?
Repeat my answer.
Yeah, you mean the lab frame.
What?
You mean the lab
there's
frame.
Additional to it. You're just saying a singular word over and over again. So if you're not going to listen to what I'm saying, then I'm not going to talk to you. Because you're not going to be able to draw a conclusion if you're not hearing what I'm saying, or interpreting it, or internalizing it, or hearing it in any meaningful way.
You said that the lab frame is where you see the correct energy of the train. Right? Like, yeah, I think I'm muted.
So yeah, just you're not muted. Just waiting for you to repeat back to me what I said. You can go back to the replay
That the lab frame is where
and then repeat it.
That the lab frame is
If
where
you're not
you
going to
see the
repeat,
correct
if you're not going to repeat all of it, and you're just going to keep repeating, you're just going to try and repeat like one singular part, then there's nothing more to discuss.
Well, I'm asking like what else is different in the train example other than the total energy?
That's a completely different question now. Like,
Well,
dude,
maybe
I'm not-
ZZ
I'm
Pop,
not-
maybe a way to
this
just
is-
kind of to recenter. Like, could
this
you
is
maybe
some
just
kind of fucking
give a
game.
Steelman? Well, ZZ Pop, could you maybe just give a Steelman your best understanding of a Steelman of his position? So I think he's trying to see if you understand what he's saying. Do you want to just do it?
Well, what Alan has shown accurately is that in the reference frame of the train has no momentum, no horizontal momentum, no horizontal velocity, no horizontal kinetic energy, and in the lab frame it does, and that these numbers come out differently from each other. And he's pointing out that these numbers come out differently from each other between these two reference frames. And then he's saying, I'm not saying the full scope of what he said. So I'm asking, what else am I missing here then? About
momentum,
this scenario.
the horizontal momentum component isn't some frame dependent fake thing. The only thing that allows for that prediction to be made is when it's with respect to the lab frame to get the total amount. You're saying, but you can, just stop. But you're saying, but we can use relative motion frames to use what it is for at that time. That's not the point. That I don't disagree with that. That's not the point. The point here is that there's one supreme frame that's making the correct prediction every time in every scenario. So for the train example specifically, right, we agree on the force that's being felt, F equals ma in that frame. You can throw the ball up, calculate how long it's going to take to fall down. But the difference is the horizontal momentum component, and that also leads to a difference in the energy prediction for the horizontal component. Mm-hmm. That's the point. It's not that they're different. It's that one frame completes the analysis, and it doesn't have to, and it never leads to any contradiction. If you do the analysis from the train frame, you're missing a component.
I think our entire disagreement just comes down then to the use of the word contradiction, because I don't see why missing the horizontal velocity is a contradiction. Like, that's not what I understand the word contradiction to mean. Like, a contradiction
because
would
all
mean
frames are not equivalent. All frames are not equivalent. That's the contradiction. Saying, but if we analyze it through relative motion at the time and we have this specific amount, then it's correct for that at that moment. What I'm saying is that with respect to the lab frame, it's not. There is a more complete analysis that's done with respect to the lab frame. That hasn't been superseded here. That's and your what your goal would have to be is to supersede that, to show that all frames are truly relative. Right? Because what this is showing, what I'm showing, is that they're not. They're all relative to the lab frame. They're not all relative to each other with no consequence. Otherwise, you'd be able to make the correct horizontal velocity component.
I mean, I don't think it's. I am 100% comfortable with the statement that different frames of reference measure objects as having different velocities and energies. So,
are you comfortable saying that only with respect to the lab frame, the full analysis is complete with no additional terms, contradictions, or physically meaningless answers?
What's physically meaningless inside the train, though?
Well, it's not just the train. There's a whole scope of scenarios to do the analysis with. It's not just.
Those are more interesting because they didn't. So,
are you comfortable saying that only with respect to the lab frame, the full analysis is complete with no additional terms, contradictions, or physically meaningless answers?
What's physically meaningless inside the train, though?
Well, it's not just the train. There's a whole scope of scenarios to do the analysis with. It's not just.
Those are more interesting.
It's not just. One second, dude. How are you going to start talking in the middle of me talking, brother? I don't care what you find interesting in the thing. We're talking about the full scope of the analysis for every scenario where this applies, right? All the scenarios that you didn't read or that we're not talking about are still at play here. They're all only the lab frame makes the correct prediction every time in every scenario for everything. So when a contradiction for a mass difference isn't shown here, so it's in a different analysis. Only one frame makes it correct every time. That's the point here. So this going back and forth circular is not leading to any meaningful conclusion.
Which is the design, of course.
Saying I don't. So your concession then is that you can distinguish between inertial frames.
Distinguish between them in terms of velocities. Yes, that's fine.
Nah, dog. In terms of the fucking dynamic analysis that we just did.
No, but I'm asking,
Hello? Hello? Is this thing on? Dude, all
what's
right.
different in the dynamics
That's
between
insane.
on the train and off the train? The
No
ball goes up and
unrefuted.
it comes
Thank
back
you.
down. Yeah.
Can I ask how you know that the Earth is not on another train?
Yeah, that's kind of where I'm going.
Yeah.
Oh yeah, where are you going, Wesley?
Can I ask you how you know that Earth isn't on another train?
How can we know the Earth isn't on another train?
Yep.
Through the
Newton's bucket makes the correct prediction for number one. Like that, like dude, if you
Yeah, I know it's hard. It's a hard thing to think of. Relative frames are hard to think about, but there's something that's real about it too. So I understand your point.
No.
But if you don't know that, you don't know that
if we
absolutely. I know you
the
got to
answer
interrupt.
was in Newton's
I know you got to
bucket,
interrupt.
Wesley.
I know you got to interrupt.
Yes,
but
yes,
Wesley,
but
no,
because
you have
the answer, Wesley,
Okay.
because the answer was in Newton's bucket. It was the starting premise. That's how we know. You're now just proposing another what if, as if the original thing wasn't covered.
So you don't know for sure. You're just making an assumption. That's fine. I agree. We have to do that sometimes.
No, that's not, Wesley. That's not what I said. And now you're just putting words in my mouth.
Okay,
I
then tell me
the
what the
starting
Newton's
premise
bucket.
of Newton's bucket.
Yeah.
The Earth is stationary, and making predictions with respect to the Earth being stationary leads to the full scope of what the energy predictions are. So if you're saying that the Earth is on another train, what you would have to do is somehow establish that there's energy being present where there isn't any. So in the scenario with the pendulum,
how would we do that?
So in the example of the pendulum, right? What you could do is you could get a thermal camera, measure the pendulum, see if there's an excess of heat coming off of it. Like whatever sort of energy dissipation or whatever you would have to do, you could try and measure that, but that's never measured. There's never any excess. There's nothing.
Or I could get off the Earth or I could get off the Earth and get into another frame, right? And measure it then, right?
Have you done that? Have you done Newton's bucket anywhere else?
Yeah,
right. Could I hold on a second? Could I do that? It's just the same example as you. You're on the train, and then you get off the train to measure it. And now I'm on the Earth. Now I get off the Earth to make sure that there's nothing else there, right?
No, incorrect. Wesley, we already covered this earlier. If you were to go into another frame and then try to say that, okay, now the Earth is doing the moving and we're going to go and analyze it from this frame, you would be contradicting the already established results. So in your hypothetical, like you haven't even done that. So the hypothetical doesn't even falsify the null hypothesis. You need to show where the energy predictions are wrong, or another frame that satisfies all the predictions the same way that the lab frame did, that's in relative motion.
Okay, so if we could do that, then you would retract what you're saying, right?
Yes, that is the challenge.
Okay. All right, I just want to make sure that's what you're saying. So that's fair then. Thanks.
Yes. That is yes. To be clear, sorry for being short with you. That is the exact point, and we went over that. That's why we started with all of that. So when you came in and was like, "Well, what if it's moving and you don't know it?" Well, then there would be you would have to substantiate that.
Well, right. That's what we're saying from. That's what we're saying from
through some sort of prediction that we're not being able to satisfy.
Yeah, that's what Daz's original point was, going to Mars or going to the moon and doing this experiment, right? We could do that, right? You would agree if we could do that, that would be valid.
Yeah.
Okay.
But it would again contradict the already established for the frame, so.
And just one other question that might be better. So would it matter to this to demonstrate Newton's bucket on the moving train?
No, because there's going to be a horizontal component that's not being accounted for with respect to the lab frame.
How do you know there's not a horizontal component in the Earth frame then? I agree with you 100% what you just said.
But how do you substantiate that there is by showing that the lab frame as stationary makes the incorrect prediction? That's what this whole thing is about, bro.
Yeah, go to the
all
moon
you
and
have
do
to
it.
do.
Yes, go to the moon and do it. Just like you step off the train to do it on the Earth, now step off the Earth and do it somewhere else and see if the Earth is moving and see if you get the same things.
I look forward to you going off of the Earth and doing that and reporting back to us what happens.
We can get moon calculations. They've done this. It's not that hard. I will look for it for next Prezi that you do.
I want a video of a guy doing it on the moon.
Oh, there we go with the moving of the goalposts.
We could calculate hypotheticals all day.
No, people that have actually been there. That's my point. Or the Mars rover, right?
Oh, they went there and did Newton's bucket?
So, right. So you believe in the equivalence.
Did they play golf? No, I'm specifically showing that there's not an equivalence.
Well, your buddy in chat has been talking about Newton's and some other, I can't remember what the Kepler's equivalence. So now all of a sudden there's no equivalence.
That's kinematics. We're talking about dynamics. Hold on, no, hold on one second.
The moving of the goalpost is saying the thing that on the moon is the same thing.
Hey, this is between us, Gal. You can come in next.
1 second. Yeah. You're talking about a difference of kinematics, which is Kepler's laws, and dynamics. This is a separate issue. In kinematics, relative motion is always true. In dynamics, it's not. That's what we showed here.
Okay. All right. I'm gonna go. I'll get the research. So I'll do my research and I'll pull that up. But now you've suddenly moved it to where I need a video recording of it being done. Right. Just want to make sure that's what you'll accept if there's a video of it.
And if you're saying an experiment took place on the moon, there's only one place anyone's ever measured a rotating bucket of water.
Okay, so if we do it right, then you'd be okay with it. That's all I'm saying. It seems like you're being fair about it, so that's all I'm saying.
Indubitably.
I just want to ask for some clarity on this point about the bucket, because if the bucket is a very important test that establishes that there's something correct or preferable about the lab frame, but we can do the bucket test on the train, then, doesn't that also establish that the train is a valid frame? I'm just trying to understand what's the criteria here.
So the criteria is all all five dynamic analysis, F equals MA, P equals MV, energy, so KE plus PE, Euler and Lagrange, Euler, Lagrange, and Hamiltonian all satisfy the conservation laws for the total amount of the energy in the system.
But just to be clear, though, the conservation laws are satisfied on the train. The total energy is different.
There's a horizontal component that's missing. So unless you can satisfy all these criteria,
that's conflating things.
Bro, it's just the same criteria that the lab frame satisfied throughout the whole thing. That's it.
Conservation of energy means that the total starting energy and the total ending energy equal each other, that no energy has been lost or gained. So if two different frames disagree on what the starting energy is, but they both agree that energy has been conserved, then that's the agreement there. So that's why I was saying that energy conservation still holds on the train. The total amount of energy might be different, but both frames agree that whatever the total amount of energy is, it has been conserved.
And only one frame correctly predicts the total amount of horizontal component. So if you did Newton's bucket on the train, same exact issue. There's going to be a missing horizontal component for momentum and energy.
I thought Newton's bucket, though, was about the shape of the water in the bucket.
Oh, I thought it was about rotating with respect to a stationary frame and then putting it on another frame and then doing the comparison. So that's what you changed it to, and that's the consequences of it, is you still get left over with a term that's not going to get you the correct answer. That's why the scope of the analysis is all the dynamic predictions available, right? And only one frame satisfies all of them without any contradictions.
So what I'm trying to ask is, other than the total energy, is there any other issue with the train? Because we do have F equals MA on the train. We do have the force of gravity as GM on the train.
It doesn't make the correct predictions for energy.
For total energy, right?
Correct. Only one frame.
But otherwise the train frame is good on all these other accounts. Like, I'm not hearing any other issue you have with the train frame other than the total horizontal energy.
Only one issue is needed. Like, it's not like I need
I don't think 7 or 8
per. Oh, it is grossly an issue because it's what distinguishes the difference between the two frames. The distinguishing factor is the difference between those two. That's what distinguishes
I don't
the
think
frames.
I don't think it's a difference that is an issue. So that's fine. So that's the point of disagreement here.
That's just like your opinion, Big Lebowski.
Yeah,
well, it's just your opinion too. I mean, it's like
I'm here to. No, it's not. It's a null hypothesis that hasn't been falsified. You're just asking random questions at this point, essentially, and also while simultaneously agreeing with me that that you can distinguish between inertial frames, which is hilariously
only with regard to this one factor, which I don't think other matters to anything else.
So the dynamic predictions don't mean anything. They're okay.
Dynamics are about forces, though, and we're not talking about forces. We're just talking about a constant velocity.
Dynamics is about predictions of motion and energy predictions and conservation and all of that. That's why all of these equations are included. Trying to confine it to one separate analysis, make it seem like the others don't matter. They're all tied together, bud.
I mean, I'm looking at what you wrote here, and you wrote that FG is the same in both frames. On the train.
My contention isn't with FG. There's a distinction between the energy
with the total
differences.
Energy. And what I'm saying is the total energy is not part of the dynamics.
What I'm saying is that's retarded. And on top of that, you need to show how a frame that you're in somehow satisfies the prediction that my frame is mutually exclusively showing and is the distinguishing factor between your so-called inertial frame. That's what needs to be done here. This whole like, oh, I don't think it's that big of a deal. You're not addressing the actual argument. This is the actual argument. There's a difference between these frames.
I mean, the word, we can go to like the dictionary of what the word dynamics means. Like, the total energy is not part of the definition of the dynamics of a system.
Dude, full dynamic analysis. Do you disagree that all these equations are related to dynamics and energy conservation and energy of a system, the total amounts of the things that would be needed? The
energy conservation and total energy are different concepts.
Are you able to falsify the null hypothesis to show that your frame has the correct energy prediction, or no?
I don't even understand what it would mean to be correct. How the total energy could or could not be a correct number.
It would be the amount that matches the lab frame.
Yeah.
Go ahead.
I have a question. So, like on Earth, we have plate tectonics, right? Those create a lot of energy. Those create a lot of.
Hang on 1 second, Pinky. 1 second, Pinky. 1 second. To round off your point, you're like, oh, I don't know how it could be possibly correct when the momentum matches what the train's velocity is.
But if velocity is relative, then momentum is relative. Like, I'm just saying that, like, it's fully self-consistent.
The train doesn't have
relative together,
dude. It's not relative to anything else. It's a dude on a train throwing a ball up. So it's only relative to the train and to the lab frame. So if it was relative to another train, it would be a different value that wouldn't be the total value of the energy relative to the lab frame, which is why it's distinctly different.
Yeah, which is fine.
It's not fine in the mainstream paradigm.
No, it definitely is. The mainstream paradigm is that total kinetic energy is reference frame dependent. And I get that you reject the mainstream paradigm, but like, the mainstream paradigm is that total kinetic energy is reference frame dependent.
And there's only one frame that satisfies all of that and makes the correct prediction every single time, which has not been refuted here at all.
All right. So my question is, when you have two like plates moving, like plate tectonics, and they collide with each other. There's a bunch of energy. Which of those two plates is the preferred Earth preferred frame?
Nice.
That's a good question. Although I wouldn't consider like, so let's take the plate tectonics thing as it is, right? And let's say they move by like, whatever amount, and then they're done moving. Like, how does that work? Are they continuously moving or what?
Yeah, I think they move all the time, and some of them are moving in. Like the one plate is going underneath the other plate. You know what I mean? It's slow, but they can't both be the preferred frame if they're moving it relative to each other.
Well, they're attached to the Earth overall as a whole. So I would say if there's any disagreement like that, like it's, moving a little bit and coming back, that, I mean, I don't even know if that's even a real thing, dude. It's like you're saying that it's not the preferred frame, but the total amount is just going to be the total amount of both of them summed together. And to do that already implies like a summation of like relative to a frame. So it's not like your question's not like leading to a different thing. It's like, what's the total amount of these two events relative to the whole? So it's not like a different scenario.
Well, it reminds me of an idea of like, what is the lab frame during an earthquake kind of question.
Right. Yeah. Dude, so, okay, that's fair. Yeah. So during an earthquake, your lab frame would have a little jitter to it.
Yeah. It'd be waving around.
Yeah. But yeah, barring any earthquake or anything like that, it's, not moving. And then of course, doing the summation of both, like of the collision of the plates or whatever, wouldn't be relative to a different frame. Like it's a part of the total whole. So you would just add them together, and adding them together would be like an absolute value in the sense of the full Newtonian of like, you're going to add two things together.
Okay, so it sounds like the answer is the correct frame is it's not like one plate or the other. There's a different frame that's like maybe deeper down in Earth.
Just the Earth as a whole.
So it's like the average of all the plates.
Nope, it's just all the Earth. Some like seismic vibration and whatnot wouldn't be like a different reference frame. You would sum them together for the total magnitude. And in doing that, it would be relative to Earth. So it wouldn't be relative to a different part of Earth. It would just be relative to Earth.
All right. My understanding was that the plate, like the continents, are actually moving slowly. I know it's slow. Maybe it's like so slow that it doesn't matter for science. But if two continents are moving or two plates are moving in opposite directions, I don't see how you could say that they're both you're gonna have a lab on one, a lab on the other one, right? You can't say that they're both the same because they're moving towards each other. If you left them there for thousands of years, eventually they would collide with each other.
Yeah, but they're both still attached to the Earth itself, right? So it's not like they're distinctly different, like two separate, like actual different bodies in space. You know what I mean? That aren't connected by anything.
I mean, I think they're touching Earth below, but they're moving. So, like, I think the plates move.
So yeah, you would.
I have to read more on it. I don't know that much about it.
Yeah, but in any case, you would still just sum whatever that is relative to the lab frame, like to the Earth itself. So it still wouldn't really change anything.
Well, I was thinking if you have like a point in space, and I don't mean outer space like NASA's thing, I'm just talking about on Earth, like a point, like we're all existing in some space ourselves right now, like our bodies, like we're at that actual point. Would that be said to be the lab frame, like that actual point in space, as it were? Because then, then you have the ground, which could be moving, like he's talking about, like either plates, or like I guess technically an avalanche or a earthquake or something. So is the lab frame like considered to be like sea level? Obviously, it wouldn't the sea level on the ground, sea level on the water, or a point in space. Like, what is considered to be the lab frame in your view on that? Like, that's being related to.
Yeah. So wherever you are doing the experiment, like that's where the lab frame would be.
Well, it's like the point in space. Like if I was doing Newton's bucket in my house and you were doing it in your house, we would both be in the lab frame, but you would be in your coordinates or whatever at your house. I would be at my house,
Yeah.
but we'd both be doing it, but we'd both be in the lab frame. So is the lab frame like basically like the point in space, like, and I could even get into like ether and all that, but even if we don't go ether, just like that point in the XYZ coordinate of like just air, reality, just the medium that we're in?
No, it would be anywhere on Earth specifically. Like if you were not attached to the Earth, you would not be in the lab frame.
So if you did it in like above the Earth, it wouldn't count. You have to be like touching the ground, basically.
Correct. You're not attached to the Earth. You are moving relative to the lab frame.
Would you say the lab frame has to do with ether, like the actual medium, or?
Nope. The lab frame would just be the Earth itself, but you could use, in regard to electromagnetic propagation, you would use the light medium as like a mathematical, as not only a mathematical frame, but the preferred frame for light to propagate in at a constant velocity. Like that would be like what it would be conceptualized as.
Yeah. Just last question on this. What
like a yeah. Oh, sorry. Go ahead.
Oh, go ahead.
I was just going to say, so it would serve as like a math reference point for like describing light, like V over C. When you do V over C, the C would be, light's speed in a vacuum, essentially. So if you take the vacuum properties, the reciprocal of those gives you the speed of light. So if you were to say that there was a medium and that light was traveling through it, in that medium, and the lowest point of that medium would be what the vacuum properties are, that would be what the speed of light is. So when you reference a velocity over C, you're referencing what the speed of light is relative to that velocity. Or you're measuring what that velocity is relative to the speed of light, and that'll give you the actual change in the in the wavelength and frequency of light, like similar to Doppler shift. It's just V over C. So like that's what it would mean. That's what it would mean mathematically. And then like physical reality, it would serve as as an actual medium for light to propagate it.
Yeah. I hear you on that. And in terms of like the ether, but what if you were out on the water? Is there a lab frame out on the ocean?
Your lab frame would move with the waves. I think the point of the lab frame is that it's not moving. So if you were doing an experiment that was motion sensitive, like ambient background, vibrations, etc., wouldn't be present. So like you could have a lab frame, on a boat, but I guess it would depend if your experiment, required, what level of sensitivity to that motion that it would be susceptible to.
Well, because that just makes me think of his question with the plates, the tectonic plates thing. Because like the ocean is always moving, the plates they claim are moving like that, even though very slow. But it just reminded me of that. Like if the lab frame is on the ground, then if the ground could be in motion, like an earthquake type thing, then it's just kind of interesting, like how the lab frame is exactly defined.
Yeah, like if your experiment or measurement wasn't measuring the vibration of an earthquake, i.e., the movement of the lab frame, then all other experiments that are measuring motion and shit aren't going to, that wouldn't be part of it, because that would only be like a specific event that occurs, that's affecting it over a certain time, where in all other scenarios it's actually stationary. So if you were doing something that didn't require, sensitivity or whatever, I guess you could use a boat in the water as a frame.
But it actually shows that there is a difference in the moving versus not moving. So it actually goes further to really the point of a lot of what you were presenting on, which is how if you were in an earthquake, you wouldn't get the right prediction because the Earth is actually in motion. Whereas if the Earth is still, you'd get the actual stationary result, or coming from that baseline.
But to be clear, I wasn't talking about vibrations. Like they actually move. I posted in chat. It's like one, depending on the continent, it's like 1 to 8 centimeters per year. So they are all moving relative to each other. It's not a lot, but they are moving. Not vibrating.
Yeah, well, we were covering both though. So like that amount of motion and also earthquakes. So like an earthquake would be more vibratory. But yeah, in any case, if the amount of the fluctuations of the plates isn't enough to cause any noticeable disagreement with the actual experiment, I mean, technically, you could account for it, I suppose, if you took the mass of that plate and added did an integral of what that momentum would be over a year or whatever for that distance traveled. Like, you could absolutely add it to it.
I mean, we should, right? If we want ultra precision, you should do that because they are moving.
No. If you want to add it, you can. I'm not.
I mean, a couple centimeters a year. I mean, have you really confirmed that yourself? No, for the first part. But
No, I haven't. I have not measured the
second.
movement myself of the continents.
All right, but even if it was happening centimeters, that's like extremely minute. And that's
Yeah, I think
overall.
I
have a
think what they
question.
do is they measure, like you go to where a fault line is, and then you can put markers up and see, how one set of land moves relative to the other. I think if you're doing if you're a scientist working in plate tectonics, it would be a big deal, right? Because those centimeters is what causes earthquakes.
What's really interesting too about fault lines, real quick, while we're on that, is I'm like 97% sure, I haven't looked this up in a while, but I'm pretty sure that the LIGO observatories are built on 2 fault lines, and they're supposed to be like, super sensitive and stuff. So it's pretty funny if they chose 2 fault lines to build it on.
So can I ask? Aren't you presuming that the Earth is still in all of these? Right. Your base presumption is that the Earth is not moving.
Correct.
Okay. So all of this is affirming the consequent. No. How is it not? I guess.
Because it's a null hypothesis. So we're actually assuming that the opposite is true for our hypothesis. And then our null hypothesis is that the Earth is an inertial frame and it's stationary. So we would try to falsify it by showing a dynamic prediction that doesn't satisfy that, and we failed to do that. So we actually failed to falsify our null hypothesis. It's not a circular assumption. It's the outcome of mutually exclusive results.
Well, couldn't you put the lab on the train and assume that the Earth is moving below you and falsify it that way?
No.
Why not?
We went over this earlier.
Yeah, I'll listen back.
You're saying doing Newton's bucket on a train?
Yeah.
Wesley?
Yep.
Yeah, so same situation. You're going to be left with a horizontal component that's not present.
Wait, no, you say there's a horizontal component, but I'm assuming the Earth's moving below me, so there is no horizontal component.
Prove it. Prove the
Right.
Earth's moving.
I'll do the Newton's bucket. I'll do the Newton's bucket on the train. I won't show any acceleration or force in any direction, and assume that the Earth is moving, and do the same experiment you just did, or same calculations.
Yeah, and from the train frame, you're still going to make the wrong energy prediction.
How?
Because you're not going to be able to account for the horizontal velocity component.
Why are you saying there's a horizontal velocity component? I don't see any.
Are you on a train that's moving relative to the lab frame?
Isn't that what the definition?
No, the lab is on the train. The lab is on the train.
I'm sorry, say that again. The lab
is on the train, so there is no horizontal component.
No, no. The train is moving relative to the lab frame.
No, I'm saying move the lab on the train. You get the same results.
The lab isn't the place where you do that. The lab frame is what the experiment is relative to. The observer is on the train.
I know. Now switch it, and you get the same result.
No.
Why not?
What do you mean, why not?
Yeah, I'm asking you, why not?
Switch what? If the train is moving relative to the lab frame, there's a horizontal velocity component.
I know.
for
Put the
total
lab
energy
on the
of the
train.
system.
Put the lab on the train. I keep saying this, but you won't go there with me, and it's fine. But put the lab on the train.
So then the train is stationary and the Earth is moving under it? Well, then it's not
correct.
a moving train. Then it's not a moving train. Then you shouldn't call it a train. You should call it something. The whole point was
then it's not a moving train. And okay, so
right.
In addition, so if you do, so
I affirm the null hypothesis.
No, incorrect.
Yeah.
1 second.
Yes.
Let me show you where you went wrong there.
Okay.
I didn't realize that that's what you were saying, because that's absurd.
Okay.
So what you would then have to do is have the Earth rotation do the work of the train to make it move, which would lead to the incorrect results, which is what the Bennett's hiker and the pendulum and stuff show. So when you try to do that, you would have to have the Earth do the work, and that leads to the physically meaningless results where it's where the energy potential would be like rocketing off into the moon.
Why is that wrong? Why is that wrong?
Because it's physically meaningless. That's not the energy that's measured. That's
from the train. From the train, it definitely is.
Incorrect. If
You
the train
just
was doing
said
the
that
work
the lab
for
would-
if the Earth were doing the work for the train, the energy potential would be based on Earth's mass, not the train's mass. It would be the
Correct.
incorrect value. It would have an astronomical amount that isn't what's measured. The
How do you know
purpose
that's
here
not correct?
is to make because
from
it
the
isn't what's
train,
measured.
from the train's point of view, it would be perfectly correct.
Well, we measure it from the lab frame, and that's what's
Yes,
correct.
which is on the
So your
train. We've said this 3 times now. The lab is on the train.
Dude, you would have to prove through dynamic analysis that the lab frame is moving. You can't. Ta-da!
Right.
You're just assuming and asking what would happen if that were the case.
I proved
you need to show it.
I proved the null hypothesis.
Opium.
Yeah, exactly. No, you could do the Newton's bucket on the train and assume that is the stationary one.
No.
And the pendulum on the train.
No.
Why? Hold on a second.
No.
I want to get this
guys,
really clear.
Guys,
why? Hold on a second.
guys.
Let me ask my question.
Guys,
Can I ask
you
it
already
again?
asked it. The answer to your question, both of your questions, even if you do with the pendulum, is that you end up with the wrong energy prediction.
That's what you say. Tell me how.
You don't get to have a fictitious amount of energy that isn't present in the system. If a guy if a guy on a bike rides down a ramp, his potential and energy is going to be based on gravity, his mass, and the height that he started with on the ramp. It's not going to be based on Earth's mass moving up to cause his acceleration.
Yes,
He's
we
going
can
to
do
end up
that.
with an insane amount of
could do
momentum
that.
that isn't present. So if you were on the train and you were trying to do Newton's bucket with a moving lab frame, you would have an insane amount of momentum that isn't present.
So you say. So Alan says. Prove me how I'm wrong.
So through dynamic analysis, as shown here,
you
you need
just
to
say
prove
the
how you're
number is too
correct.
big.
Yo.
All you're saying is the number is too big.
It's not just that the number's too big; it's imaginary and not present. It's a
How do you
fictitious
know?
amount that's not real.
How do you know?
Because nothing behaves like that. No one's ever measured a pendulum having excess heat energy coming off of it because Earth rotation. There's nothing ever that's harnessable from this fictitious amount of energy that you're suggesting is present in the system
large amount
that you
of
don't
mass.
have a problem with.
Yeah, because you have a large amount of mass.
The large amount of mass is what creates it, and it's not present in any measurable system relative to the lab frame. So you need to measure that amount and show that it's what's being present relative to the lab frame, and that would show that the lab frame is
Right.
wrong.
Yep,
You're not
I
doing
do
that.
all my calculations assuming that the train or the plane is stationary, and I come up with all the numbers that work.
Incorrect.
Yeah, they're just too big. I understand you think they're too big, but that's incredulity.
It's not an issue of them being too big. It's the issue
what you
that they're
said.
not physically present. So
How do you know
yes,
that?
they're too big because they're not physically measured in the system. When you say,
Yes, they
how do
are.
you
From
know
the
that?
train, they
And I
are.
said, shut up for a second. And when I said, hey, you could get a thermal camera and measure the pendulum and see if it's emitting excess heat. It's not. Never been done. There's no way to harness the fictitious energy that you're referencing.
Yes,
So it
the
is
Earth
wrong.
is emitting a
That's why.
lot of heat, and it's because it's very large. So yes, it is perfectly measured in the system.
That's not even what I said in relation to. I was talking about measuring the energy of a pendulum bob swinging relative to the Earth, while you're saying that you can analyze it relative as if the Earth frame is causing the motion. And I'm saying if you do that, the astronomical amount of energy that's too big would be somehow measurable in the system. It would come off as excess heat or something. There would be some way to measure it, and that's never been done. So your task,
Wait, where's the heat coming from?
That.
Yeah, exactly.
It would just some excess, just some way to have excess energy.
No,
there's no. It would be excess energy in the system, and there's never been measured.
You're just saying
so
that.
When I gave the okay, give me an example of how. Okay. So when the pendulum swings, is it swinging with the momentum and force of the mass of the pendulum, or is it swinging with the momentum and force of the mass of the Earth? Simple question. That's how we know. That's it. That's all it is. That's how we know. When that giant number, when that ball hits a wall or impacts something, and we predict how much energy and momentum and all that it has, when we use the mass of the Earth, it would smash whatever that is to then that's not what happens.
No,
that's how we know.
It's relative.
Yes. Yep.
That's what you're missing.
Nope.
Yes.
Nope. Nope.
Yes.
It's an absolute value. That's what we're showing here in the lab frame. If it was relative, then that pendulum would smash whatever into pieces traveling with Earth's mass.
Incorrect.
As momentum.
That's incorrect. That's a misunderstanding of physics.
Yes.
Okay. I'll let some of the guys that are smarter than this. But
wait, why would the pendulum have Earth energy?
I know. It's crazy.
Oh, dude. Okay, so hold on one second. You're gonna turn around and say, "Oh, I know, lol, that's crazy." When you were just arguing that you could use Earth's mass to make the train move, bro.
Yes.
You guys are going in circles over this. I'm actually no.
The Earth is moving.
You're not gonna mute or talk over me when I'm about to exit out of here. I'm not doing that infinite DS forever, dog. So here's the issue at hand. Here's what needs to be satisfied. You guys are saying that the Earth's potentially in motion somehow, and we're not accounting for it. Okay. So you need to show how that relationship manifests in the lab frame, making the incorrect prediction. Until that's been substantiated through the dynamic analysis that have been provided here, force, momentum, energy, Euler-Lagrange, and Hamiltonians, then the null hypothesis has not been falsified for this type of analysis. Now we can get on to other experiments and measurements and stuff as we continue, but for this in particular, has not been falsified. Every single proposition here has been met with the same thing, where the energy isn't, there's some contradiction in one of these analyses that is not being present, and you could use that to differentiate which frame is unique. And in that, we've shown that the lab frame consistently makes the prediction every single time for every single measurement, or for all the types of analysis. When you use other frames moving relative to the lab frame, you end up with numbers that don't make physical sense because they're not present in the measurement. We know exactly how much momentum a ball swinging into an object is based on its momentum, based off of its mass, velocity, and height that it was dropped off of, based off of 9.8 meters per second squared. There's no astronomical amount of energy at that impact that's obliterating the object that we're like, oh, wow, the frames are equivalent. They're not equivalent. The two different outcomes emerge from this analysis. That's the point of this. The fictitious amount isn't what's measured in the lab. The heat example I was giving would be if somehow there was a translation of that excess energy of one potential way that it would manifest in the system that you could measure it. Nothing like that has ever been measured. None of this excess energy has ever been harnessed. So anyone who wants to show that relationship, that's what you would need to do to falsify the null hypothesis. Now we're going to wrap up here. We've been going for
I would say plate
2.5
tectonics do
hours.
that.
What? 1 second. Yeah, please interrupt me in the middle of my outro instead of waiting for me to say, "Hey, if anyone has any closing thoughts, would you like to repeat plate tectonics and substantiate something that apparently doesn't affect any lab measurement known to man?" Then, yeah, we can get to that in a second. But let me finish closing out before you just interrupt. All right. So we will be back, not next week, but the week following. I'll be out of town for the next Monday, so we won't be here for a follow-up. Now, when we return, we'll be back for a follow-up. And so if anyone has any things that they would like to present on this null hypothesis specifically, they can show their dynamic analyses. So Pinky, or what's your Finky? Finky? Finky, if you want to incorporate the dynamic movement of the plate tectonics or what have you, show that in the analysis, and you can present it. When we do our next show. So that's it for this. For tomorrow night, we'll be doing a reading night on either cosmology. Stone's going to be reading a French translation about an analysis of Maurice Allais and the Michelson-Morley experiment. And if I'm not mistaken, it's not by Allais himself; it's by someone else. If Stone's there, maybe he can.
That is correct.
He can answer. Thank you, sir. All right, so we'll be reading that tomorrow night. And then Friday, we'll see what the lads are up to on the Twitterverse. You could tap into Shane's stream if you want to catch that on the YouTube, or you can join Twitter and follow Kembo or Brian Sweet to get when that'll be out on Friday. And then we will return on the following Sunday, which I think will be the 7th. We'll return on the 7th for Globebusters for the season finale, where Stone's going to close us out there. On, I forget, what are you doing again, Stone?
Well, it's actually on LA again, but all of
the full LA breakdown.
It's also all the previous and subsequent work attached to it.
Nice, dude, nice. All right. So if anyone has any closing comments or concerns or things that they would like to touch back in on next week or what have you, the floor is now open for a couple of minutes, and then I'm going to close out the stream. But Finky, if you would like to discuss the tonics.
I just want to say real quick, these are the guys, you never know what's moving guys right here you're dealing with.
Yeah.
Even like simple things, you can just never know. You never know what's moving.
Well, that's the point, right? Relativists are supposed to be no preferred frame. Any frame's as good as the other. It's all equally good. That's supposed to be your position. When you show that it's all only equal and true in the lab frame, that's a contradiction. And no one wants to engage with that. Instead, we get endless dog shit. Whatever.
Yeah. I would highly recommend reading the first page of Einstein's 1905 paper, where he opens up talking about the laws of mechanics holding good and what he defines as an inertial frame being in uniform rectilinear motion. And the laws of mechanics are what we just used for our analysis. So all those equations that represent dynamics and energy and conservation and all of that, all of those are the laws of mechanics. So Einstein's hypothesis about how frames are indistinguishable, they're all equivalent, they're not. That's what we specifically showed here. The difference in the analysis and the measurements for whether it be kinetic energy or momentum or F equals ma or what terms need to be added to satisfy a Lagrange or Hamiltonian. None of those need to be added for the lab frame. That's what is important. If all frames are truly relative, then there's no absolute. And the difference between absolute and no absolute physics is what relativity is all about. So referencing the referencing the total momentum of a system and then saying like, oh, well, it doesn't matter, they're still all equal, relatively to one another, is not true. We just showed uniquely that relative to the lab frame, they're not all relative to one another. There's an absolute value. And that comes out of the lab frame, guys.
Awesome presentation, man. I'm looking forward to refutations or falsifications of the null hypothesis, if we're going to do things scientifically and not, whataboutism or how about this and on the moon if we call that the lab frame. They're just like actual rebuttals and refutations. So I'm looking forward to that when that happens.
Yeah, and I was mistaken earlier about moving the observer. So like anywhere on Earth would be, quote unquote, the lab frame, but the observer doing the experiment, wherever the observer is at, like those coordinates would define, if the observer is on Earth, then he's in an inertial frame, and if he's moving relative to the Earth, then he's in a non-inertial frame, essentially. So if that was confusing or whatever, there's a clarification on that. Yeah, we'll go ahead and wrap up then. Thank you guys for your time. Appreciate it. We'll see you guys next week.
Thank you, Alan.
Thank you guys.
Yes, thank you.
It's all relative and all frames are valid, and you can never know what's moving until we're in
Never know anything.
heliocentrism. Until we're in heliocentrism, then we know exactly what's moving. We know Earth's rotating, right? We know all these things as soon as you step into heliocentrism. There's a contradiction there. In one idea, you can never know what's moving. All frames are valid. It's all relative. But then in another idea of heliocentrism, you know exactly what's moving.
Yeah, one of my favorites out of that is they'll use V over C for aberration in air. And then when water was added, they're like, well, I mean, you could never really know. Like, how do you predict a change in one but not the other? You have to go through several different layers of the convolution to get to that one. But yeah, it turns out, like Jeremy was just saying, when an analysis is put forward that shows how you can differentiate between the frames, you can see that they're not truly relative to one another. Like that the relative to one anotherness is just a like an artifact of the frame differences themselves and what you're comparing it to. But in reality, like that train's moving at whatever velocity it's moving at, so it has a horizontal momentum component to it. It has a horizontal kinetic energy component. It has a full absolute value that is only represented with respect to the lab frame. All right, lads, I'm gonna go watch anime and play video games now, or whatever it is I do around here.
You put in a good day's work, Alan.
I agree, Jesse.
Jesse, if an astronaut is floating in the ISS and was able to be 100% still, not moving, just like curled up into the fetal position, right? And then decided to see if he or she could do like a somersault, would the astronaut be able to do a somersault from a static position floating in the ISS?
I mean, quite possibly. I would need the context, but yeah, I mean, you can you can like say sit on a swivel chair, and by swinging your arms and pulling them in and pushing them out, you can rotate. You can effect net rotation. So like, and very a falling cat can turn itself right side up.
Okay, so then the Earth is the astronaut in that static position in space, but it's got the conservation of momentum, and then there's some extra movement added to it, like the tides. Would that not put the Earth off balance?
What's off balance?
The tides sloshing around, making the Earth not balanced. Like a gyroscope that's off balanced would not work, right?
It would work. The only reason it's a problem for man-made gyroscopes is the shake makes the is hard on the bearings. But if it's a spinning mass that's not mounted on bearings, then it just spins exactly around its very center, and it's no problem at all.
Unless there's some movement, like you just explained, the astronaut could actually start doing a somersault with some movement, right?
Wesley, are you still there?
Yeah, I'm here. Sorry. Yeah.
All right. Maybe when these guys are done, I want to ask you something on the last topic.
I'm done.
Yeah, I'll be here.
Well, was there a finish to that, or about the somersaulting astronauts?
Well, we just wanted to know if the Earth could be put off balance by any movement whatsoever, like weather, the tides, earthquakes, tectonic plates moving. Would that shift the Earth off its like Swiss watch style axis? Conservation of momentum would be broken.
No, changing shape doesn't violate the laws of energy.
Changing the speed, he's saying. They do claim that some things do change the speed.
Yeah, the speed is changing very, very slowly. That's why they are always adding leap every so often, every so many years.
You go ahead, Gio. What did you have to say?
No, but I mean, I hear what he's saying. Like, could you do something on the Earth that you could physically change it in any noticeable way? I guess that would be some way to differentiate between sky moving or Earth moving. If you could do something to the Earth and actually change the way the sky's moving, which I don't think you can, but if somebody could show that. No, it's all good. I just was going to ask Wesley, like with the whole laboratory thing on a train, like, do you really think that doing experiments or really of any sort, like on a train, is exactly the same as on the ground?
Is it exactly the same? Of course not. But why? The only reason that we assume that the Earth is more valid is because we live here 99% of the time. So, yes, because we've lived here, we will say that's the preferred frame. But that's awfully presumptuous of us, and that's what I've learned over the years, that we can't. You could do the same exact experiment. What if we were only able to live long enough, like on a plane, for 20 minutes? Then we would use that. Like if we lived on a plane, like an ant or something, we would use that as a preferred reference frame. Or in the future, if we're living on airships and we forgot about what the Earth was like, we'd use the airships as a preferred reference frame. So it's harder to think about, but yeah, I think it's mighty presumptuous if we do that.
All right, but if you say you have like a laboratory that's in like, one of those it's like a square building that you can move around. What are those called? The name of them? They're like often like on like trucks, and you can move them, little like pods. Anyways, if you had some kind of like a pod thing that was like a laboratory, and I mean, not really like a mobile home thing. It's not really on wheels, but you can move it. You know, you can put it up on the back of a truck and then move it if you want. Anyways, if you had like a laboratory like that, and then you literally put that on a train going 80 miles an hour or whatever speed, you could even make it one of those hyper fast trains. Versus if you had that thing on the ground, just at rest. And then whatever physics experiments you're doing in that laboratory, you know, whatever the little humans are and they're doing stuff. Let's say they have no windows. Let's just say for the moment, no windows at all. And then they're doing various physics experiments. And I realize it would be dependent on like, okay, what kind of experiments? But either way, if they're doing experiments, and then you were going to calculate all of the physics involved. So your job would be to calculate all the physics. So if that thing was on the ground and it was just stationary, you wouldn't really have to account for too much outside of it. Maybe a little bit of wind, possibly, if there was an earthquake or something, or if there was like some kind of massive movement of the earth, maybe. But other than that, like you wouldn't really have to, other than like maybe the temperature, barometer, you know, wind that might be brushing up against it, you could calculate for that. Whereas if it's on a train, now imagine it's even on the inside of the train, so I guess you don't, because I realize if it's literally on a train, the wind's blowing, you would probably agree, okay, of course it's going to be massively different. But let's just say that thing is inside the train, so like technically it's blocking, you know, the train is doing the blocking of the wind. Are you suggesting that if your job was to calculate all the physics with the one that's on the train versus not on the train, that there would not be a difference? Because that's kind of like part of what was all being discussed in terms of the lab frame being the one that actually gives the predictions of the physics.
He had to jump, but he asked us to take over for him. Yeah, if the train was going on a perfectly smooth, flat, you know, level track, not veering to the right or the left or going up or down, riding smoothly along, the windows are shut, you would be completely unable to determine if and how fast the train was going from within the train without looking out and referencing something else outside the train.
What about our hearing?
From inside or outside the train?
Yeah, let's say, how soundproof is the cabin? Is it 10 out of 10 soundproof?
Well, it doesn't matter. If you were using sound from outside the train, then you could determine your velocity relative to whatever was making or reflecting sound outside the train. But from inside the train, no sound that was originated and contained entirely within the train would tell you whether the train was even moving at all or how fast.
I agree. Thank you.
I've been on the smoothest train in China, magnetic levitation train, and the pressure is different. You know when you're moving because the pressure is different.
Interesting.
The air pressure? What pressure?
Yeah, like did your ears pop or did you?
Yeah, the air pressure goes up. You can feel it. Yeah, you can feel the air pressure changes.
They probably do they pressurize the cabin for those kinds of speeds? They might, but you can tell you're moving. It's just walking from the front to the back or back to the front. You're sensitive enough. You can tell.
No, they don't pressurize.
You're going with it or against it, like a walkway beneath you. It's definitely different.
It's not like an airplane. Yeah, I got sore ears, like painful ears, when they were going too fast because they don't pressurize the cabins.
Even on an airplane, it's different too.
I don't know. I've walked forward and back in a flying airplane, a jetliner. It just felt like I was walking.
And you know, if you sit at the back of the airplane, the air is not as good as at the front of the airplane. You can tell the difference in the air.
Well,
I mean, if you put a blindfold on someone and you had them walk on the ground, completely stationary, regular ground, had them walk, then you have them walk on either an airplane or a train from the back to the front of the plane or train, versus or a bus even, or from the front to the back. I would say, like in terms of the human body being able to pick it up, it is somewhat subtle. Like you'd have to be pretty sensitive to a degree. Like somebody who's really not paying attention might possibly not notice, because you are, like if you're going 500 miles an hour in an airplane and you're in the back of it, you just went to the bathroom and you step out and you take one step forward. You're going 500 and you're using the 500 mile an hour speed that you're already going because you're already up to speed with it. Like you got on it and you went along the seat that you were in, the floor that you were in started going faster and faster, 50 miles an hour, 60, 70, 80, all the way up to 500. And it slowly took you up to that speed. But the minute you step forward, you're going 500 miles an hour plus a little bit more speed. So there's going to be a little bit more resistance there because you're actually going a faster speed in relation to the thing that you're on. Now, granted, you don't have all the wind in your face because obviously the fuselage is taking care of a lot of that. And then if you were to go to the front of that and start walking backwards, when you're going 500, but then you're going a little slower, a little under 500, the first step you take walking backwards. But somebody who's sensitive and aware can be able to pick that difference up. And I would be willing to put that to the test too. If you blindfolded people and some would be able to decipher it.
I can feel it. Like you don't have to be that sensitive. It's actually really obvious that you're moving. Yeah, sure, you can balance a coin on its side on the table, no problem. But when you start walking on the plane in either direction, you're going to tell that you're moving.
Yeah. If you're in a bus going 60 miles an hour and you run from the front to the back, you'll pick up a lot more momentum, even if it's not accelerating. Like you'll almost feel like you're going to smash into the back really fast. And then if you run the other way, it's sort of like running uphill. Now you got to also factor in if there's any actual like slope to the ground, which sometimes there is in an airplane or in a bus as well. But it's like you're going against it or with it. Just like when you're on one of those walkways at the airport where it takes you faster. If you walk with it or against it, it's completely noticeably different.
Well, you'd be multiple ways you could check this, like setting a glass of water on a table in front of you when you're sitting down. That water should indicate that there's some force, moving in the direction that you're going. Or you could use your accelerometer on your phone and you could check it. You should be able to detect that if it's there.
You could pick. What do you mean, walking on an airplane, picking up with an accelerometer? I mean, that'll pick it up.
No, just sitting still. Just sitting still on the plane. You should be able to detect it sitting still if there's a force in one direction or the other.
There is. I mean, what you're saying, if you're maintaining speed or going faster or slower, or if you're just maintaining the same speed, you mean?
If you're just sitting in the chair in your seat on the plane, you should be able to detect a force in one direction or the other with an accelerometer or just a glass of water sitting on the table in front of you.
Well, water probably would not be able to pick it up if the water's, I mean, depending on how sensitive, because the water's already going, let's say 500 miles an hour, and it's being kept at that, and then the container of the glass would be maintaining that 500. What do you think you would pick up in the water? Like a whole vortex motion? I mean, I think the way to pick it up, because I realize what mainstream physics says about this, and it would have to be like debunked on the mainstream level, even outside of like these combos here, or whatever people think that they're right or wrong, or winning, losing debates. Like outside of all that, there is like an actual paradigm there. And so I've wondered if it could be shown, more clearly with like a gravimeter, the ones that drop a ball. And if you drop the ball, it would actually fall a little bit behind when you're in the moving train or the moving.
NASA, is that NASA? Are you saying that that you wouldn't be able to measure the movement of the train?
If it's not accelerating, you're not going to pick up any forward or backward force of any kind. If you're going at a constant speed and you're inside a sealed up vessel, like the chamber, the compartment on an aircraft, there's not going to be any forces there except down.
We are using the Earth. We're using the train as an analogy, like swapping places with the Earth. So now you're basically saying that you wouldn't be able to measure the Earth moving, right?
What if we get the velocity? What if we get the velocity up to 9 Gs? Right, we're on the 1 G, but what if we get it at a constant 9 G? Are we going to feel it physiologically?
Yeah, if we get going thousands of miles an hour.
Yeah, velocity is not measured in Gs, Eden. That's an acceleration, right?
Oh yes, yeah, thank you.
Yeah.
No, but he's saying if you accelerate it up to that.
Yeah, and then we just lock it in there. Do you think we would no longer? Let's say we get to 9 Gs. Are we going to presume we are no longer going to feel the physiological effects?
Once you're accelerating, yeah. So you can get in a jet fighter and do an 8G turn or something like that and then level out at constant velocity. You're back to square one, right? You don't know how fast you're going.
Yeah, but if you walk against the parasail, you go to Disneyland and you go on that, what's it called, with the horses that go up and down. If you walk backwards on that, you'd know that you're going in the opposite direction.
If you shut your eyes, how would you know?
You can feel it.
Yeah, have you ever like the moving walkways at an airport or like a mall or something like that? Everyone in here has probably been on those. I mean, maybe in different countries they don't have them, but where you're walking normally on the ground and then you get on that thing, and if you just keep walking like a good brisk walk, the minute you get on it, whoa, you kind of like pick up speed, and you're like, you can feel the airflow against your face, obviously, and then you can obviously notice, and you're a little tipsy too sometimes right when you get on it because it's a change of speed and all that. But then once you're on it, if you walk with it versus against it, now I know there's the differences of the airflow, so to like test it further, you'd almost have to build some kind of shield around you or something, but there is a noticeable different physics. Like when you're walking with it, you're being propelled through the medium, let's just say, air, whatever you think the medium of that we live in, like meaning not the ground, not the celestials, but everything in between the ground and celestials, whatever we call that, the air, the medium, whatever, space, etc. You're either propagating faster through it when you walk with it, or you're walking against it. And even though your relative speed based on the walkway is the same of your steps, there is a difference in the physics of whether you're propelling forward or through the medium faster or slower by going against it.
I suggest that if you actually shut your eyes in that scenario, and be careful, so if you got on the walk, so when you step on the walkway, you get accelerated, right? So straight away there's that. But once you're on the walkway and up to speed, if you shut your eyes and walked, you would have no perception of your motion.
Daz and I are going to be at the hospital. We're going to be at the airport with blindfolds on. People are going to be like, "What are you doing?" Be like, "Oh, we're just testing some stationary Earth theories."
Well, they get arrested or end up in the hospital, right?
Yeah. But dude, okay. So the wind flow, you obviously would feel. So I think most people, like even if you did this test, I think most would be able to because of the flow of the wind against your face. So that alone, but you'd have to somehow control for that. But you're saying that, okay, if you blindfolded me and we actually did this, or if you did it, are you claiming that you would not be able to decipher the difference? Walking with a moving walkway or against it?
Yeah, because it's like the same as deal when you're in an aircraft, right? You can walk up and down the aircraft that's doing 900 miles an hour, and it doesn't feel any different than when you're on the taxiway.
No, I'm suggesting that there is a difference, though. Because like if you're going 900 on that airplane, when you start going walking with it, going from the back to the front, you're actually picking up. You're going a faster rate through the medium. Now, granted, if you have all the wind blocked, you're not going to have the wind flow against you, but you're still going to have the viscosity of space, essentially.
So would you think the faster that it goes, the more of that force would be present?
Well, it would be like a proportion. You're saying if you're going 500, then you take a step and you're going 500 point something miles an hour versus if you're going 2,000 miles an hour and then you move a little faster?
Yeah.
So the state of affairs here is that no instrument known to mankind is able to detect what we're claiming that humans here can detect, and no humans have been reported to have detected it in a double-blind test. So there we go.
Who's tested that? Who's even tried? Are you just saying no one's tried it?
I'm just saying there to date there are no double-blind tests that have been reported where a human was able to detect what you're claiming could be detected by a human.
But has anyone even tried?